Okay. A very good evening to all of you. On behalf of Department of Physics, Bethune College, I welcome all the participants, eminent speakers, our special guest, or other distinguished personalities to the 6th Ananta Kumar Sarker and Snehalata Sarker one-day seminar for the advancement of the knowledge in physics, organized by Department of Physics, Bethune College. In this inaugural session, I would like to requesting our head of the department, Professor Kamal Kanti Som, to deliver the welcome address. Kamala, please.
আমাকে দেখা যাচ্ছে বা শোনা যাচ্ছে গোপা?
হ্যাঁ, দেখা যাচ্ছে, শোনাও যাচ্ছে, একদম ঠিক আছে।
ঠিক আছে। ভেরি গুড আফটারনুন না ইভিনিং বলবো জানি না, যাই হোক, এনিওয়ে all on behalf of Bethune College, Department of Physics, I welcome you all in this 6th Ananta Kumar Sarker, Snehalata Sarker one-day seminar for advancement in the knowledge of physics. আমি বাংলাতেই বলি, আমাদের স্টুডেন্টরাও আছে, অনেকে প্রচুর স্টুডেন্ট জয়েন করেছে দেখতে পাচ্ছি। তো আমাদের প্রিন্সিপাল ম্যাডাম প্রফেসর কৃষ্ণা রায়েরই আজকে থাকার কথা ছিল, উনি থাকতেও চেয়েছিলেন, কিন্তু ওনার একটা সাডেন একটা খুব ইম্পর্টেন্ট এনগেজমেন্ট এসে যাওয়ার জন্য উনি থাকতে পারছেন না। তো অন বিহাফ অফ হার অলসো আমি সবাইকে আজকের এই অনুষ্ঠানে ওয়েলকাম জানাই। বিশেষ করে আমাদের যে দুজন স্পিকার আজকে আছেন, খুব এমিনেন্ট স্পিকার, প্রফেসর চিন্ময় কুমার ঘোষ, ফরমার ডিরেক্টর Indira Gandhi National Open University in various positions উনি ছিলেন, এবং উনি ওয়েস্ট বেঙ্গল অ্যান্ড সিকিম রিজিওনাল সেন্টারের ডিরেক্টর হিসেবেও কাজ করেছেন দীর্ঘদিন। খুব বিজি উনি, তবুও তার মধ্যে আমাদের অ্যাকসেপ্টেশন মানে আমাদের ইনভিটেশন উনি অ্যাকসেপ্ট করেছেন, তার জন্য আমরা খুবই কৃতজ্ঞ তার কাছে, স্যারের কাছে। এছাড়াও আছেন আমাদের মধ্যে আইআইটির প্রফেসর, খড়গপুর আইআইটি ডিপার্টমেন্ট অফ ফিজিক্স এর প্রফেসর সমিত কুমার রে, ফরমার ডিরেক্টর এস.এন. বোস ন্যাশনাল সেন্টার ফর বেসিক সায়েন্স। প্রফেসর রায় অনেকদিন এস.এন. বোস ন্যাশনাল সেন্টারের ডিরেক্টর হিসেবে কাজ করেছেন, এবং কোয়ান্টাম ম্যাটারে উনি খুব রিনাউন্ড একজন সায়েন্টিস্ট, আমাদের দেশের লিডিং সায়েন্টিস্ট, এবং অনেক ভালো কাজ আছে। এবং এই দুজনের কাছ থেকে আমরা আশা করছি যে আজকে আমরা খুব মূল্যবান কিছু আলোচনা শুনতে পাবো। এছাড়াও আজকে অন্নপূর্ণাদি, যিনি এই টোটাল আমাদের এই যে অনুষ্ঠানটা, এটাকে যার অনুপ্রেরণায় শুরু হয়েছিল বা যার আর্থিক সাহায্য দিয়ে শুরু হয়েছিল, সেই অন্নপূর্ণাদি আমাদের মধ্যে আছেন। এটা আমাদের খুবই আনন্দের যে অন্নপূর্ণাদি আমাদের বারবার বলেছিলেন যে অনলাইন মোডে, আমি অনেক বয়স হয়ে গেছে, অনলাইন মোডে আমি চাইছি না, অনলাইন মোডে আমি পারবো না জয়েন করতে, কিন্তু অন্নপূর্ণাদি কিন্তু প্রথম দিকে অনেকের আগেই খুব স্বচ্ছন্দভাবে জয়েন করেছেন। এবং অন্নপূর্ণাদি অ্যাট দ্য এজ অফ আই থিঙ্ক ওভার 90 বছরের উপরে বয়স, এই বয়সেও উনি যে ভীষণ উৎসাহী এবং আমাদের প্রতিটা মুহূর্তে আমাদের উৎসাহ দেন, আমাদের অনুপ্রেরণা। উনি আমাদের বেথুন কলেজেই উনি একসময় ছিলেন এখানে লিডার হিসেবে, এবং বেথুন কলেজের যে ফিজিক্সে যে অনার্স কারিকুলামটা শুরু হয়েছিল 1963 মোস্ট প্রবাবলি, তো সেইটাতে 60-তে পর 67 আই এম নট শিওর, এইরকম পিরিয়ডে, তো সেই সময় অন্নপূর্ণাদি সেখানে একটা লিডিং রোল নিয়েছিল। এবং আফটার রিটায়ারমেন্ট উনি কিন্তু থেমে থাকেননি, প্রচুর বই বিজ্ঞান নিয়ে গবেষণা, বিজ্ঞান নিয়ে প্রচুর বই লেখালেখি করেন, এখনো করেন। এবং প্রত্যেকবারই উনি আসেন আমাদের, গত বছর আমরা এটা করতে পারিনি ডিউ টু প্যান্ডেমিক সিচুয়েশন। অন্নপূর্ণাদি খুব চেয়েছিলেন যে, আমরা গত বছরও একবার অনলাইনে ব্যাপারটা করার কথা ভেবেছিলাম, কিন্তু অন্নপূর্ণাদি খুব চেয়েছিলেন যে অফলাইনে করবেন। কারণটা খুবই স্বাভাবিক যে অফলাইনে করলে সামনাসামনি দেখা হয়, দুটো কথা হয়, যেটা অন্নপূর্ণাদি খুব চান। উনি যখনই সুযোগ পান, শরীর যদি ঠিক থাকে, উনি কলেজে চলে আসেন। সেই গত 1-1.5 বছর আসতে পারেননি, ভীষণ মনমরা হয়ে থাকেন। তো উনি চেয়েছিলেন যে অফলাইনে হোক, কিন্তু সেটাও হয়নি গত বছর, সেই জন্য গত বছরেরটা আমাদের একটা গ্যাপ হয়ে গেছে। এবছরও আমরা ভেবেছিলাম এক সময় যে আর কটা দিন ওয়েট করি, অফলাইনে যদি করা যায়, কিন্তু আলটিমেটলি দেখা গেল যে সেটা কতদিন ওয়েট করতে হবে কেউ জানে না। সেই জন্য আমরা অনলাইনেই করার কথা ভাবলাম, এবং অনলাইনেও আমি দেখলাম যে অন্নপূর্ণাদি খুব স্বচ্ছন্দ। অন্নপূর্ণাদিকে আমাদের আন্তরিক ধন্যবাদ ও কৃতজ্ঞতা ও নমস্কার জানাই। আজকে আমাদের আমন্ত্রণে বিশেষ অতিথি হিসেবে এসেছেন প্রফেসর মমতা রায়। প্রফেসর মমতা রায়কে আমাদের টিচাররা এবং অনেক স্টুডেন্টরা অনেকেই চেনে। প্রফেসর মমতা রায় এখন বর্তমানে ওয়েস্ট বেঙ্গল স্টেট কাউন্সিল অফ হায়ার এডুকেশনের ভাইস চেয়ারম্যান একাডেমিক এর দায়িত্ব সামলাচ্ছেন। খুবই ব্যস্ত, তার মধ্যেও আমি একবার বলাতেই উনি সঙ্গে সঙ্গে রাজি হয়ে গেছেন এবং উনি জয়েন করেছেন। আমি ভীষণভাবে আনন্দিত এবং কৃতজ্ঞ প্রফেসর রায়ের কাছে। ইনফ্যাক্ট এই যে এন্ডাউমেন্ট লেকচারটা, এটা 2015 সালে শুরু হয়েছিল, 2015-এ, এবং তখন মমতা রায় বেসন কলেজের প্রিন্সিপাল ছিলেন। তো আমার পরিষ্কার মনে আছে যে একদিন অন্নপূর্ণা দিন আসলেন, এসে কথা বললেন, এবং আমিও ছিলাম তখন। মমতা রায় সেই প্রথম দিন থেকে, প্রফেসর মমতা রায় যেভাবে উৎসাহ দিয়েছেন এবং যেভাবে তার উদ্যোগে এবং অন্নপূর্ণাদির উদ্যোগে এটা খুব সুষ্ঠুভাবে শুরু হয়েছিল, সেই জন্য প্রফেসর রায়ের কাছে আমরা আজও কৃতজ্ঞ। প্রফেসর মমতা রায় এসেছেন, আমরা খুবই গর্বিত এবং ধন্য। আর তাছাড়াও বিভিন্ন কলেজ থেকে যেসব পার্টিসিপেন্টরা, আমাদের কলেজের স্টুডেন্টরা তো আছেই, বাইরের কলেজেরও আমি দেখতে পাচ্ছি কিছু পার্টিসিপেন্ট আছে। যেসব পার্টিসিপেন্টরা স্টুডেন্ট আর টিচার্স বোথ যারা আছেন, তাদেরকে আমি আমাদের বেথুন কলেজের পক্ষ থেকে আমন্ত্রণ জানাই। আর যাদের কথা না বললেই নয়, আমাদের ফিজিক্স ডিপার্টমেন্টের কলেজের তো একটা অ্যালুমনি অ্যাসোসিয়েশন আছেই, আমাদের ফিজিক্স ডিপার্টমেন্টেরও একটা ছোট অ্যালুমনি অ্যাসোসিয়েশন আছে, ফিজিক্স অ্যালুমনি অ্যাসোসিয়েশন আমরা বলি। সেখানে আমাদের প্রাক্তনীরা আসেন, খুব ডিপার্টমেন্টের সঙ্গে খুব ক্লোজলি তারা রিলেটেড। বিভিন্ন অ্যাক্টিভিটিতে ডিপার্টমেন্টের তারা সবসময় আমাদেরকে উৎসাহ দেন এবং আমরাও তাদের কাছ থেকে পরামর্শ নিই। ইনফ্যাক্ট এই এন্ডাউমেন্ট লেকচারটার যে পরিচালনা, তার দায়িত্বের একটা সিংহভাগ তারাও সেটা পালন করেন, এবং এটা একটা জয়েন্ট কোলাবোরেশন বিটুইন ডিপার্টমেন্ট অফ ফিজিক্স প্রেজেন্ট অ্যান্ড পাস্ট, এরকম ভাবে আমরা বলতে পারি। কেন পাস্ট যারা স্টুডেন্ট আছেন, শুক্লাদি, শাশ্বতীদি, মঞ্জুষাদি, আমি সবার নাম করছি না, প্রত্যেকে আমাদের সাথে ভীষণভাবে বিভিন্ন অ্যাক্টিভিটিতে থাকেন। তো তাদের প্রত্যেককে আমি বেথুন কলেজের ফিজিক্স ডিপার্টমেন্টের পক্ষ থেকে এবং বেথুন কলেজের প্রিন্সিপাল প্রফেসর কৃষ্ণা রায়ের পক্ষ থেকে আজকের এই সেমিনারে আমন্ত্রণ জানাই। ধন্যবাদ।
Thank you, Kamalda. Thank you for your warm welcome address. Akash Babu, I cannot start my video. It's showing that your video is disabled by the host. Akash Babu? Okay.
রাইট, কথা দেখা যাচ্ছে।
Okay. Today, we are very glad to have with us a very special guest, Professor Mamata Rai, Vice Chairman, Academic, West Bengal State Council of Higher Education. She is also former principal of Bethune College. In spite of her very busy schedule, she has kindly consented to be with us today. Thank you, madam. Thank you for being with us. Now, I would like to request Professor Mamata Rai to deliver her speech. Madam, please.
Am I audible, Kumar?
Yes, madam.
Am I audible?
Yes, yes. It's fluctuating little bit, but it's okay now. Hello?
হ্যাঁ ম্যাডাম, শোনা যাচ্ছিল তো?
আচ্ছা শোনা, আচ্ছা ঠিক আছে। Good afternoon to all of you. It's very nice that I meet you, though on virtual mode, but it is always nice to meet you. The reason why I readily accepted to attend this, Dr. Kamal Shom's head of the Department of Physics, his request to attend this program. There are two reasons for this. One is because of this endowment, when Dr. Shom brought Annapurnadi to my chamber, I remember vividly, I had the opportunity to meet an extraordinary teacher, first of all, and then also a devoted physicist. Annapurnadi's commitment to her discipline, her commitment to her students, and still her desire to connect to all acquaintances always impressed me. Secondly, this is the first reason that I would have some opportunity to meet Annapurnadi, though on virtual mode, but it is still as if a real feeling. I'm imagining that I am sitting in the Centenary Hall where you used to organize this, and a lot of students are sitting and very eminent physicists are coming to deliver their addresses. So first, congratulate Dr. Kamal Shom and her very able colleagues in the Department of Physics who are consistently organizing this seminar for last 5 years, and this year even through virtual mode, but inviting two eminent physicists on very vital topics, one on Albert Einstein. Perhaps we could understand one or two things because this great scientist had very great multifaceted personality, because of which we can understand one or two things, not technical physics, but the other human faces of this great personality. These are the two reasons why I am here. And once again, my humble regard to Dr. Annapurna Sarker, who has instituted this endowment in memory, endowment seminar in memory of her parents. And I have till today very good relationship with Annapurnadi. We often talk, we often exchange things like that, though everything digital. And I remember it is also an opportunity for me to remember my good days in the Bethune College campus with my colleague teachers whom I am seeing over this virtual mode. And it is reminding me those good days where we could work together, the pre-COVID days. Because of the pre-COVID period, we really enjoyed everything which we could do in a collective mode. So I wish that the seminar will continue years after years. And this is also an opportunity where we could say, when it was conducted on mode, the students of the Department of Physics who are still very much attached to the college. This is an opportunity to pay my respect to all of them. And it is an opportunity, again, to wish the very best to the college and especially to the young students of this college who might one day become again very, very good world-class scientists. And this seminar, the two eminent speakers, their speeches, I am sure will enlighten quite a number of students apart from the teachers and all other listeners from other colleges. And they will remember forever in their life what they will be learning and listening today. So thank you. And Annapurnadi, once again, namaskar. আপনার সাথে আবার পরে কথা হবে. Thank you. Thank you very much for inviting me. Thank you.
Thank you, madam, for your nice speech. Your words and your presence also always inspires us Thank you, madam, once again for being with us. Now, we have reached to a very important part of this seminar. We will now hear and learn about the life of three great personalities, Dr. Annapurna Sarker and her parents, late Ananta Kumar Sarker and late Snehalata Sarker. I would like to request Dr. Shukla Chakraborty, our alumni, who is currently working at Ananda Mohan College as associate professor, to deliver her speech on a brief note about the life of late Ananta Kumar Sarker, late Snehalata Sarker, and Dr. Annapurna Sarker. Shukla Di, please start your speech.
অধ্যাপিকা অন্নপূর্ণা দি আমাদের অধ্যাপিকা ছিলেন। ওনারই বাবা এবং মায়ের স্মরণে এই লেকচারটা উনি অ্যারেঞ্জ করার জন্য 6 বছর আগে আর কি এই এন্ডাওমেন্ট লেকচারের জন্য ডিপার্টমেন্টে কিছু টাকা দিয়েছিলেন এবং উনি বলে দিয়েছিলেন যে কিভাবে সেই লেকচার গুলো করা হবে। প্রথমে একটি লেকচার অ্যারেঞ্জ করা হতো, তারপরে ওনার ইচ্ছা অনুযায়ী দুটি বক্তৃতায়, একটি বক্তৃতা কোনো একজন বিজ্ঞানীর ওপর আর অন্য বক্তৃতাটি একটি ফিজিক্সেরই একটি টেকনোলজিক্যাল মানে টেকনিক্যাল বিষয়ের ওপর যাতে করা হয় সেই মতোই উনি বলে দিয়েছিলেন। এবং তার সাথে ওনার ইচ্ছা অনুযায়ী ওনার বাবা মার সম্পর্কে কিছু বলার কথা প্রতি বছরই থাকে। এবার সেই বিষয়টি আমার ওপর দায়িত্ব পড়েছে। অধ্যাপিকা অন্নপূর্ণা সরকারের বাবা শ্রী অনন্ত কুমার সরকার ছিলেন পূর্ববঙ্গের অর্থাৎ বর্তমান বাংলাদেশের বরিশাল জেলার একটি ছোট জায়গার জমিদার শ্রী পূর্ণচন্দ্র সরকারের কনিষ্ঠ সন্তান। পূর্ণচন্দ্র দান ধ্যানের জন্য স্বনামধন্য ছিলেন। অনন্ত কুমারের ছিল 5 দাদা ও 1 দিদি। জমি জমা, ধন দৌলত ইত্যাদির কোনো পার্থিব বিষয়ের ওপর অনন্ত কুমারের কোনোদিন আকর্ষণ ছিল না। তিনি দাদাদের কাছে কোনোদিন জমিদারির কোনো অংশ বা অর্থ চাইতে পারেননি, যার ফলে উনি তার ন্যায্য পাওনা থেকে বঞ্চিত হয়েছেন। অঙ্কশাস্ত্রে এবং ইংরাজি সাহিত্যে ছিল অনন্ত কুমারের অগাধ পাণ্ডিত্য। বলা যেতে পারে he was a born genius in mathematics. বিভিন্ন ধরনের কঠিন কঠিন গাণিতিক সমস্যা নতুন নতুন উপায়ে সমাধান করার নেশা ছিল তার। তিনি পেশাগতভাবে একজন অ্যাডভোকেট হলেও he was a professor by nature and temperament. আশ্চর্যের বিষয় হলো অ্যাডভোকেট হিসেবে তিনি তার মক্কেলদের কাছে কখনো কোনো পারিশ্রমিক দাবি করতেন না। তারা নিজে থেকে যেটুকু দিতেন তাই তিনি গ্রহণ করতেন খুশি হয়ে। ঢাকা শহরে তার খুব খ্যাতি ছিল। দায়রা আদালতের সিভিল লয়ের সূক্ষ্ম বিশ্লেষণ করতে পারতেন বলে। হয়তো এর মূলে ছিল তার হাইলি ম্যাথমেটিক্যাল ব্রেন। তিনি বিনা পারিশ্রমিকে ঢাকার এক নামকরা জমিদারের বিরুদ্ধে মামলা করে জমিদারের অধীনস্থ নিপীড়িত এক ঘোড়ার গাড়ির গাড়োয়ানকে জিতিয়ে দিয়েছিলেন। পরিবর্তে তিনি পেয়েছিলেন প্রচুর খ্যাতি, সতীর্থদের প্রশংসা আর সেই গাড়োয়ানের প্রাণ ভরা শ্রদ্ধা, ভালোবাসা ও সেবা। তিনি তার আইনজীবীকে প্রতিদিন সকালে ঘড়ি ধরে আদালতে পৌঁছে দিতেন, আবার বিকেলে বাড়ি নিয়ে আসতেন। অন্য সময়ের অবকাশে তিনি চাইতেন তার আইনজীবীর ছেলে মেয়েদের তার ঘোড়ার গাড়ি দিয়ে সহায়তা করতে, কিন্তু ছেলেমেয়েরা সেটা গ্রহণ করার প্রয়োজনীয়তা অনুভব করেনি। আবার আর একদিকে অনেক আইএএস পরীক্ষার্থী আসতো অনন্ত কুমারের কাছে অঙ্ক ও ইংরাজি পড়তে। তিনি বিনা পারিশ্রমিকে তাদেরকে সন্তান স্নেহে পড়াতেন। তার কাছে শিক্ষা লাভ করে আইএএস পরীক্ষায় উত্তীর্ণ হয়ে তারা জজ, ম্যাজিস্ট্রেট হিসেবে বা অন্যান্য উচ্চ পদে প্রতিষ্ঠা লাভ করেন। অনন্ত কুমার সারা জীবন কাটিয়েছেন গৃহী সন্ন্যাসীর মতো। তার সাধক চেতা মন কেবল ছুটে বেরিয়েছে জ্ঞানের সন্ধানে, আর অর্জিত জ্ঞানকে তিনি সর্বসাধারণের মাঝে ছড়িয়ে দিয়ে এক আনন্দলোকের সন্ধানে ব্রতী ছিলেন, যেখানে সব অর্থ, বিষয়, সম্পত্তি নিরর্থক বলে মনে হতো তার। আর এই আদর্শের জন্যই তিনি মহান, সকলের কাছে শ্রদ্ধেয়। অন্নপূর্ণাদের মা শ্রীমতী স্নেহলতা সরকার ছিলেন অত্যন্ত ব্যক্তিত্ব সম্পন্না, অসীম সাহসী, তেজস্বিনী, ধর্মপ্রাণা, সমাজসেবিকা, পরোপকারী এবং দয়াশীল মহিলা। তিনি পূর্ববঙ্গের এক সম্ভ্রান্ত পরিবারে জন্মগ্রহণ করেন। তার পিতা শ্রী যোগেন্দ্রনাথ গুহ ঠাকুরতা ছিলেন ঢাকা শহরের একজন নামকরা ক্রিমিনাল লয়ার। তার বুদ্ধিদীপ্ত ও আভিজাত্যপূর্ণ চেহারায় এবং উদাত্ত কণ্ঠে আইনের তর্জমায় বিচারালয় সচকিত হয়ে উঠত। তারই জ্যেষ্ঠ সন্তান সুযোগ্য স্নেহলতা। স্নেহলতার স্বামী জ্ঞানের সাধনায় নিমগ্ন থাকায় সংসারের প্রতি উদাসীন ছিলেন, তাই স্নেহলতার ওপরেই ছিল সংসার চালনা করার দায়িত্ব। সাংসারিক নানা কাজ সামলেও তিনি ছেলে মেয়েদের পড়াশোনার খোঁজ খবর রাখতেন। ম্যাট্রিকুলেশন পরীক্ষার শেষ পর্যন্ত তিনি ছেলে মেয়েদের পড়াশোনায় সাহায্য করে গেছেন। পরিচিত মহলে কাউকে হাসপাতালে নিয়ে যাবার লোক না থাকলে অথবা কোনো মৃত ব্যক্তিকে শ্মশানে নিয়ে যাবার কেউ না থাকলে তিনি উদ্যোগ নিয়ে পাড়ার ছেলেদের সঙ্গে নিয়ে প্রয়োজনীয় ব্যবস্থা গ্রহণ করতেন এবং নিজেও প্রয়োজন অনুযায়ী হাসপাতাল বা শ্মশানে উপস্থিত থাকতেন। প্রতিদিন ভোর 4টে ঘুম থেকে উঠে অনেকটা পথ হেঁটে ঢাকা শহরের পাশ দিয়ে বয়ে যাওয়া বুড়িগঙ্গা নদীতে স্নান করতে যেতেন এবং গঙ্গা স্নান সেরে গঙ্গা জল ও ফুল বেলপাতা নিয়ে ঘরে ফিরে পুজোয় বসতেন। তিনি ছিলেন লোকনাথ ব্রহ্মচারীর প্রধান শিষ্য ভিখারীনাথ ব্রহ্মচারীর শিষ্যা। পূজা শেষে সাংসারিক নানা কাজ, স্বামী ও সন্তানদের নিজ নিজ কাজে বেরোনোর সহায়তার পর নিজের স্নানাহার সমাপ্ত হলে বেরিয়ে পড়তেন পরিচিত মহিলাদের লেখাপড়া শেখার ব্যাপারে উদ্বুদ্ধ করতে। তার আন্তরিক অনুপ্রেরণা ও সহযোগিতার ফলে বহু গৃহবধূ লেখাপড়ায় আগ্রহী হয়ে নানাবিধ জ্ঞানার্জনে ব্রতী হয়েছিলেন। সেটা 1930-এর দশক। তার এই আন্তরিক প্রচেষ্টাকে অ্যাডাল্ট এডুকেশনের গোড়াপত্তন হিসেবে অভিহিত করা যেতেই পারে। স্নেহলতা সাংসারিক সব রকম কাজ অতিশয় দক্ষতার সঙ্গে সম্পন্ন করতেন, আবার সারাদিনের নানাবিধ ব্যস্ততার শেষে অনেক রাত্রি পর্যন্ত বই পড়ার অভ্যাস ছিল তার। বিস্মিত হতে হয় এই ভেবে যে কোথা থেকে তিনি পেতেন এত আত্মবিশ্বাস, এত প্রাণ শক্তি ও এত মনের জোর। কিন্তু দুর্ভাগ্যজনকভাবে এক দুর্ঘটনায় শিকার হয়ে মাত্র 40 বছর বয়সে এই মহীয়সী নারীকে বিদায় নিতে হয়েছিল এই পৃথিবী থেকে। সমাজের সকল শ্রেণীর মানুষের ঘরে ঘরে নারী শিক্ষার প্রসার হলে স্নেহলতা দেবী স্বল্পদীর্ঘ জীবনের প্রয়াস সার্থকতা লাভ করবে। নমস্কার।
Thank you, Sukladi. Whenever we hear about their life, it always mesmerizes us. Now we are moving towards today's first technical session. We are very happy to have with us renowned scientist Professor Sumit Kumar Ray. Professor Sumit Kumar Ray is currently a professor in the Department of Physics, IIT Kharagpur. He has previously served as the director, S.N. Bose National Center for Basic Sciences, Kolkata, and Dean, Postgraduate and Research Studies, Head, Department of Physics, and Founder, Head, School of Nanosciences and Technology, IIT Kharagpur. His research interests are in the area of semiconductor nanostructures, quantum dots, photovoltaics, and nanophotonic devices. Professor Ray is a fellow of the National Academy of Sciences, India, Indian National Academy of Engineering, West Bengal Academy of Science and Technology, and is the recipient of INSA Young Scientist Award, UGC Homi Bhabha Award, MRSI Superconductivity and Material Science Senior Award, etc. He has published more than 350 research papers in peer-reviewed journals, 7 book chapters, and co-authored a book on strained silicon heterostructures, materials, and devices, published by IEE UK. Due to time boundary, we cannot describe many things about Professor Samit Kumar Ray, but we are very eager to hear from this renowned scientist. His lecture topic is Wonderful World of Low Dimensional Materials. I would like to request Professor Ray to start the session. Before that, I have a small announcement that Dr. Rakhi Pal, Assistant Professor, Department of Physics, Bethune College, will conduct the rest of the session. Now, I request Professor Ray to start his lecture. Sir, please.
Thank you, Professor Bhomik, for nice introduction. Am I audible?
Yes, sir. You are audible.
Okay.
And visible also.
Okay.
Yes,
So let me
okay.
first thank the organizer, particularly Professor Shom of Bethune College. I'm really privileged to be one of the speakers of today's the 6th Ananta Kumar Sarker and Snehalata Memorial Lecture. And I could learn a lot of things about their contribution to the society in general. And also let me thank their daughter, Annapurna Sarkar, for actually starting this endowment lecture. Okay, so I'm very happy. Probably I'm speaking for the first time in an environment or in a meeting in a Bethune College. It has got long history and legacy. So everything is known about that. I think the oldest women college in India and most probably in Asia as well, with a lot of illustrious alumni. I still remember that one of my classmates at IIT Kharagpur doing MSc at that time, the year of 82 to 82, was one of the students of Bethune College, though we are not in touch because that time there was no email or Facebook. And of course, at IIT Kharagpur and SNPO Center, we used to get a lot of students, and those are actually that kind of very preferable first batch of students used to come from Bethune College for doing either master's and PhD. So I really thank the organizer and really actually acknowledge the contribution of this college for the women empowerment in India, at least. So let me now share my screen. And please check whether everything is fine and let me know. Is it okay? My screen, I've made full screen also. Is it visible?
Yes, sir, it is visible.
Okay. So I have chosen a topic. Yeah, since this is a technical lecture, that's what the organizer requested me that this should be a technical lecture. So just let me mute this. Okay, let me minimize this. Okay. So since this is a technical lecture, I have chosen a topic which is a little bit interdisciplinary, not necessarily physics, physics, chemistry, and of course I will be talking something about the materials. So there's always a, kind of a class of science we call material science. Normally, we don't encounter the material science courses in undergraduate and postgraduate courses, but normally somebody goes for a kind of a PhD or the higher end of research. This is extremely useful. And probably through this lecture, I'll say why the materials is so important and why should we go for the low dimensional materials. So I'll start with a little bit of historical perspective of materials. I think this lecture is for the students, so I have made it a little bit popular for the students. And because, of course, I mean, it's not for the teachers and the professors. So if you see the materials, which I can definitely say is the backbone of the modern civilizations. Whatever we are today, what we are getting today is behind this, there's always advancement of materials. Of course, we started about from the Stone Age about few million years ago, where that we had got only limited amount of materials which are available in the nature. And probably about 5,000 years back, actually, that human learned how to mix two materials and get an alloy of bronze by using a copper and tin. That is probably the first engineering of materials done by the human about 5,000 years ago. So the modern civilization started from the so-called Iron Age, which is about 3,000 years old. Particularly the invention of the steel, which is a very, very stronger and cheaper material, drastically changed the life of common man, because people started making big building, railway line, and many other structures by using the steel. And the steel is still going very, very high. So one of the most demanding material, particularly for the applications. Of course, today the way the science, we are more interested in physics or chemistry, we are more interested in some new material or advanced materials. So some of the materials, the classes of materials can be classified like this: is kind of a ceramic materials, what is the bone china, etc. So these are actually called the ceramic materials, but the ceramic materials has got a lot of other properties which can be used for making a lot of scientific equipments or scientific things. Semiconductor, probably I'll discuss a little bit more in my lecture because I work in this field, though I'll really not go to any research work of mine, but just try to say that what is the status and trend in these materials. Polymer also that one of the very important materials, all plastics, polymers that is used. Of course, we have the problem with lots of plastics, of course, causing the environment pollution. There is one more problem, but polymers has got a lot of applications and many other materials. And today we are talking about something new kind of materials. So this may be the new keywords for the students who are attending here. But probably we have also read in the newspaper or the news articles about something called nanomaterials. Then something called quantum is the backbone of the physics. And today probably that Professor Ghosh will be talking about Einstein, actually the founder of the quantum mechanics. In fact, the great Indian Satyendranath Bose was also one of the foremost founder of the quantum mechanics theory. So I think he will be having a touch on that. But I'll be speaking that this quantum mechanics can be used in materials also. So it can go from theoretical textbook to even to application side. So what is most important for the scientists, particularly physicists, chemists, this is really interdisciplinary. I'll not say only physics, chemistry, mathematics, biology, engineering. So to establish a relationship between the structure of the material, their properties, and their performance. So basically what we wanted to do, we always want to change the structure and make new properties and make some new materials called intelligent materials. So those materials may not be available in the nature. So we'll create some materials in the laboratory. Okay, just I start with some examples. Some breakthrough inventions. Of course, there can be thousands of them, millions of them. Many people may not agree, but these are my popular, actually. Some of the, if I choose 4, this comes in my mind because of different diversity, and they have really made a serious impact in our modern science. Of course, I have not included healthcare here. Healthcare is one of the modern inventions. That's why we are all live here today in spite of the COVID pandemic. So I just don't want to compare, but in physics, I can say some of the greatest inventions, particularly in the application side, maybe one personal computer. So of course, PC stands for a laptop. Then now we have the computer in a mobile phone. So this has really made our life very, very easy in terms of communications. Hold this internet, actually hold the so-called the IT is dependent on this PC, but the computer. But if you see, this computer is not only a computer, actually. You have got probably some hundreds of different materials are embedded in this computing system or computer system. starting from a semiconductor chip to actually that a lot of metals, lot of polymers, ceramics, I was taking some names. Even your screen, the display that you see, that is made of some kind of organic materials or polymer materials. So it's basically or some LEDs, so LEDs, LCDs, etc. So these are actually ultimately the byproduct of the development of the materials over the last probably I could say at least 100 years. Then come to the lasers. Of course, semiconductor lasers I have taken because semiconductor lasers are very, very small in size. So all our fiber optic communication through which we are talking today through internet are actually based on the semiconductor lasers because that is based on something called optical communications. And the source for the optical communications are the laser. Not only that, as you know, that lasers are used for all kind of medical applications, healthcare, I mean, what not? It's very difficult to say that what are the applications of laser, but huge amount of applications. So I have taken one applications on the some electronic device, one application on the optical device. Let me use my pointer. I can just use my pointer also. Just laser pointer. Yeah. So yeah, the next panel, the figure that you can see is the tiny LEDs actually. These are nothing but the white LEDs that you see in the Calcutta street light. That as you see that if you go to the particularly the Salt Lake, Newton, and many other areas in the what actually during the puja and other things that is decorated with all kind of lights. Called actually it's called the white LEDs. In fact, they are much more efficient, much less power hungry compared to conventional light sources. So they can solve a lot of problem about the energy. They're also actually some kind of one more variant of the lasers, we call the LEDs. Okay, just take an example of other material. So we talked about superconductor, semiconductor, we talk about optical devices. Let me take an example of something called superconductor. As the name suggests, is a highly conducts electricity, the superconduction of electricity. Actually, the resistance for a superconductor below a critical temperature is 0. So the students we can think of if you use the Ohm's law and if the resistance of a wire is 0, so you can think of how much current you can pass through that. Almost infinite amount of current you can pass. And since there is no resistance, there is no heat dissipation. So this superconductor has got a lot of applications in many other applications. One of the applications just I have shown is for magnetic levitations, which are used for very, very high speed bullet train in advanced countries. And India is also planning to have one. So the last example that I have taken actually in this case is we know that the brain, our brain is actually is that probably in terms of computational power, this is the highest computational power available that is in the earth. So the question is that we are doing a lot of things. We are making robots, we are creating artificial intelligence, we are doing so many things by writing programs, algorithms. But can we really make a brain or construct a brain in the laboratory? So that is probably in the future, in next 20, 30 years, probably the present generation of students will see that yes, you can mimic the brain. The brain means basically you have got a huge amount of memory, and all these memories are connected to different neurons and go to your CPU actually, and that ultimately actually directs you what to do. So I have taken this example. All these are actually dependent on some classes of materials which have actually really made an impact in the society or the modern science. So let me go to the next slide. Okay, so now what is the trend? Before going to low dimension, actually I have defined what is low dimension one. I'll come to that in later on. So first is, can you just miniaturize the material? Of course, if you think of your computer, so it was very, very bulky and heavy. Now if you miniaturize, now you have got something in your mobile phone. So miniaturization is always good in terms of its weight, power, its cost, everything. So that is one of the trends, that you miniaturize the things and change its property to get some exotic properties or unusual properties. That is one trend. The second trend, as I said, that can you make the material smart? Whether the materials itself, due to its property, can take some decision, because there is nobody to take the decision. Material itself has to take a decision. In fact, a lot of materials actually take the decision by themselves. You think of the airplane wing actually, that, and you know that when an airplane fly, what is the outside temperature? But there is no actually that freezing up. There is no freezing of ice on the airplane blade or the wings. Otherwise, the plane will not run. So the material itself has got some kind of property that it can unfreeze themselves. Similarly, if you are trying to make a civil engineer trying to make a building which is actually earthquake prone, so the building itself has got some property that even in a earthquake with a Richter scale of 7 or 8, nothing happens to the structure. So there can be hundreds of examples of that. I've just taken a few of them. The other important is that, as I said, that we have to really now think of some environment-friendly materials, because the environment is going to be a big problem probably in the next few generations. And there's always a predictions that about next 100 years or 200 years, whether there is enough fuel or this earth will be actually fully polluted by the carbon dioxide emissions. So even as I took the example of the plastics or the so-called polymers, so one of the main problem is whether these plastics are not degradable. A plastic, if you put in the ground right now, it remains there for 100 years. So definitely you have to think of some kind of a plastics which are biodegradable. That means should degrade within few years. It should be degrade by photodegradation, like a light or temperature. So these are some kind of a invention that must come through the next generation. And of course, these material science are also, because biology is also one of the most important things, because most of the particularly in the healthcare and the biological sciences, we can learn a lot of things from the actual nature. So we can, like for example, if you take the silk of a spider that you see in our household, we don't know how actually strong that tissue is. In fact, that tissue of the spider silk is much more stronger than any fiber that is available in the nature. So it's the strongest advanced laboratory. Yeah, so you can learn from nature and try to mimic these things and make new materials. Okay, there can be unending examples, so I should not probably go on everything, so because of the lack of the time. So the question is that before going to introduce today's topic on low dimensions, the question is, where are we heading in material? The example that I have taken is the miniaturization, that the scaling of materials. Of course, if you make something small is always beautiful, but not only that, if you make it smaller, it has got a lot of other properties, which we call the bountiful. And the main actually application come for the main lessons may come for the nature, because nature has made a lot of things very, very small. We'll come to some applications of that. Okay, now I can see that, okay, sorry, my heading may not be able to see. So now I introduce a kind of a material actually, as not a material actually, one form of material. We know that is the materials we have got solid phase, liquid phase, and the vapor phase. But even in the solid phase, we can make the material can be completely three-dimensional, or if you basically if you reduce the one of the dimensions of the material, suppose x, y, z, if you reduce the z dimension, that is the thickness of the materials become very, very thin. Now, if the materials become very thin, now the question is that if the materials is very thin, there is lots of advantages. Of course, the materials that will be dealing with is very, very costly. So can you actually coat a material or a deposit of material on something so the costly material can be deposited on a very cheap substrate? The example, this is called actually a thin film. So this is very, very important, particularly for the low dimensional materials. Rather, this is the first step towards the low dimensional materials. You can take lots of examples that you see that you paint a car actually. You paint a car not only for its good look, you paint a car to prevent from corrosion and oxidations. Otherwise, there will be a lot of corrosions and it will be actually to damage the car body. Similarly, the watch that you use or actually regularly is a very nice golden color. Of course, this is not a gold. Actually, gold is very costly. This is some kind of materials whose optical property is like gold. Okay, and you make a thin coating of gold on your watch, so the gold looks bright in color as well as it protects it from oxidation. Or even take the example of your simple mirror that you use in our daily this thing. This is actually made of silver coated or aluminum coated actually glass, which are nothing but the mirrors. So these are some of the low-end applications, but of course there are a lot of high-end applications which will come to my lecture. And from kind of a, I'll say thin film is nothing but a approach towards a two-dimensional materials. So why I'm calling two? If I say that a material has got 3 dimensions, X, Y, and Z, if we make the Z dimension very, very small, negligible compared to the X and Y directions, it is almost like a mimic like a two-dimensional material. I'll come to that example later. Okay, so one more solution has to come from again from the materials. That is basically our problem of environment pollution and carbon dioxide emission. So this is which is called the energy and the environment in the broad sense. This is really a very, very hot topic for the research and in terms of materials. So I've just taken a international energy data to predictions of the requirement of energy and the carbon dioxide emission that will happen up even in 2030. So in the left side actually shows that million ton equivalent of oil. So this is the left side scale is a million ton equivalent of oil. And the right side, the graph shows that million tons or megatons of carbon dioxide emission. So in 21, we are here somewhere in today. So you see how much million tons of carbon dioxide you are emitting every day, every year. Actually, this is annual actually, and how much million tons of oil equivalent that you are using. So the problem is that most of them are coming from the fossil fuel, and as you see, this our requirement is increasing almost exponential. So this is the problem of the modern civilizations. That one way we want a very, very civilized life, we want a life with a so-called communications, transport, and many other comforts, but actually it is giving a lot of problems to the nature. So the biggest problem is that probably you've heard that our fossil fuel reserve in the actually global is limited. So what will happen beyond 2030 or 2040? So you have to have a lot of other energy sources which are called renewable energy sources, which can come from sun, wind, ocean, etc. So this is a kind of a very, very hot problem. It's going on for the last 30 years, but still a lot of challenges are there. Okay, nuclear energy is, of course, is a very, very good source, but the problem is that still we are not able to solve how to tackle the nuclear waste. So this is an open problem probably for the next 50 years or so. Okay, so one of them I'll discuss a little bit that just maybe highlight is the solar cell. Solar cell is actually probably you know that if you put sunshine on a device, actually that it creates electricity. So there's is made of something like a silicon. This is the first solar cell was made in 1954, and you could convert actually that converting light energy into electrical energy. And a conventional solar cell looks like something like that. So it is a 3-dimensional material, semiconductor material called silicon. Okay, sometimes we call them bulk material. So as you know that all what is p-n junctions, etc., that you have already done in your class 12, etc., or even in the BSc. So it's nothing but a p-n junction, and when the light falls on this, it generates actually a lot of electron and hole pairs, and they are collected in the external circuit and give rise to some voltage and current. So you get some kind of power. So a modern solar cell looks like something like this. But the problem is that material consumptions in this 3-dimensional solar cell is extremely high. So the silicon is a semiconductor, very high purity semiconductor, very, very costly. Then there's the abundance of every material is limited in the Earth's crust. So you have to think of something that how can you reduce the use of the materials and almost get the same performance. That is actually what is the aim of the thin film. So that is the example that I gave you, that instead of using a material of a very, very high thickness, can you coat a material, suppose you coat a plastics or maybe metals or any other we call them substrate, any other material, and put coat them with some materials, some semiconductor materials, which can be used as a solar cell. In that case, solar cell will be flexible. Solar cell can be made from roll to roll. As you see that is actually probably the next few generations in the future. It is already available commercially in the market. that you can put a just plastic solar cells coated with semiconductor materials. So this is called the thin films. So these are thin film solar cells. And not only that, you see, this is one of the hearts in the rural places. You can just coat with some materials like a paint in your car and create some kind of a very, very large area solar cell. So these are some of the probably the way of solving the energy issues in the future. So the materials has to be thinner, materials has to be cheap, and materials has to be very, very large area. Otherwise, you cannot make silicon solar cells to actually tackle the energy issues of this world. So okay, so again, this is a very common example. Normally, we took that. What is the effect of scaling? That means you come from a large scale to low scales or to a kind of miniaturization or scaling actually. So that is the whole this thing of today's lecture. This is the first computer, the baby computer at Manchester University, UK. So this is a huge room. It was 1948, as it suggests. And this was occupying the whole room. And of course, probably if you say the memory, etc., the computational power is extremely negligible. It's much, much less than what a calculator, handheld calculator can do. So now with miniaturization, we know that what we have done today. So I don't have to explain to you. Now let us say scale of things actually. What are actually the scales that we are talking about? So we know what is, suppose in the length scale, we talk about 10 to the 3 or kilometer, we know millimeter, centimeter, etc. This is typically the length scale we use. Of course, you go on increasing the scale, you go to the astrophysical scale, okay, giga, mega, etc., in terms of either energy or maybe distance. When you come to the actually lower dimensions, lower and lower dimensions, from milli to come to micro, probably this is also feasible. You can see in the microscope also some micrometer of objects. Then from micro to nano to pico to femto. So just to give example that where some of the objects that we see that we perceive is a miniaturized objects, like a human hair. Thickness of human hair is typically about 50 to 100 micrometer. On the other hand, the size, the diameter of the radius of a silicon atom. Silicon is, I have taken as an example, but take any atom in the range of only few fraction of a nanometer, about 0.2 nanometer or so. Okay, in the atomic physics, board radius of the hydrogen atom is 0.053 nanometer. So basically, the question is that you are coming from actually that mega scale material to so-called the mini scale to micro scale to nano scale, and ultimately you are going to the limit of so-called the size of atom or size of molecule that I will discuss afterwards. Okay, so this is a nice story. I am sure that many of you, of course, read this particularly, the story of the Feynman. Now, the question that always being asked that who first used the term or invented the term nano? So nobody knows, but of course, everybody believes that the physicist believes the first vision of so-called the kind of this of nano, etc., came from this Feynman lectures in American Physical Society in a Caltech in 1960 actually. So he's thinking, see, this is the Feynman's quote here. So Feynman says in the lecture that, and there is a device on the market, they tell me, by which you can write the Lord's Prayer on the head of a pin. A pin means the pin that we use for our household pin. But he says that remember, Feynman was a theoretical physicist. He was not experimental physicist or engineer. But at that time, he had a vision that in next 40 years or so, in 2000 or so, that we have really some technology. And he thought that why can't we write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin? So the title of his lecture was that there is plenty of room at the bottom. That means you go down and down, you scale things from some scale to again some other scales. And he thought that if you go to something in the nanometer scale, actually you can get a lot of things. So the four visions that he had in that lecture, actually I have again presenting here. He said that, of course, that for 24 volumes of Encyclopedia Britannica, so if you assume that each encyclopedia contains about 1,000 pages, you see the size of the memory is, each page is about 44 kilobyte in size, and about 1,000 pages, if we assume about 24, is about 100 megabyte or so. And now today, if you go to market, you can easily buy a pen drive of about 32 GB, 16 GB easily in the market without any problem. Then his vision was that, can we manipulate individual atoms to make new structures? Because you know that atom is like the backbones of all structures. If you start with atoms, you make a molecule, and from the molecules, you make some kind of a new materials. So he was thinking, can we really manipulate these individual atoms to make new materials? In fact, today this is possible in the laboratory. People could do with a new kind of just one of the example I have taken, new kind of microscopes called scanning tunneling microscope, which works in the actually theory of the quantum tunneling, and you can make a nice microscope, and that can be used to manipulate atoms on the surface of a material. Of course, that time it thought in 1959 or 1960, actually there was no so-called integrated circuit, that power was extremely low. So he was thinking whether we can make building circuits on the scale of nanometers for more powerful computers, which is actually real in today's world. And he also thought there must be some kind of nanostructures in biological systems. So the main problem at that time, that why since he actually proposed that in the lecture, people could not verify experimentally. That time we didn't have any microscope. We don't have any very high quality microscope to visualize atoms. Now, for the students, you know that in a optical microscope that you use in your laboratory, that works with maybe think of a visible wavelength, okay, 400 nanometer or so. And now we are talking about something called 10 nanometer, 5 nanometer or so. So definitely, you know, due to the Raleigh's limit, you cannot actually image object with a 5 nanometer or 10 nanometer size with a 300 nanometer or 400 nanometer wavelength. So you have to have some sources whose wavelength is very, very low. Today, it is possible by scanning electron microscopes. Actually, they are known as scanning electron microscope, tunneling electron microscope, then the STM. So whatever he predicted that time is probably all real today, or could be achievable today. So of course, you must read the biography if you have not done so, that Feynman biography. Sincerely, surely you are joking, Mr. Feynman. He has got some weird ideas, and he used to throw them, and people used to think that what he's speaking on. Okay, so now with some background on these things, and that why should we use a low dimensional materials? Now let me define a little bit that what is actually that low dimensions. As I said, that if you take a crystal or if you take any kind of a bulk material that is available in Earth's crust, actually they are all three-dimensional materials. Okay. Now, question: if you reduce the dimension of the material, as I said, the thin film, the thickness of the material is very, very small. Then we call it a thin film, particular thickness. But that is not really a two-dimensional material. And in the definition of the physics, the two-dimensional material or a low-dimensional material will be defined like this: if the size of one of the dimensions are comparable to the de Broglie wavelength. I know that you all know what is the de Broglie wavelength of electrons or carriers, or for any other matter. Actually, this is a matter wave. You also know I just described you what is the Bohr radius of hydrogen atom. But if you find out Bohr radius of some other solid, it will be all different. So if you say the size is, if one of the dimension is less or comparable to these parameters, you can say that particularly what we have, that you have some kind of reduced dimensionality in that particular directions. For the example, if you take a thin film, and if you reduce the thickness to very, very small range, in the range of 10 nanometer or so, or less than 10 nanometer, usually, just for example, I'm calling it, we are defining as a two-dimensional materials. That means you have got X direction, we have got Y direction, and the Z direction is very, very thin. Actually, what happens if you take electrons, suppose you are trying to say find out the resistivity or conductivity of this material, what happens? The electrons are free to move in the x and y directions, but in the z directions, since this dimension is less than the de Broglie wavelength or broad radius, the electrons now behave not as a particle, now it waves as a wave. As you know, that is the famous de Broglie hypothesis. So then in the z direction, the property of the material will be decided by the quantum property of the material, not the classical property of the material. So this is actually the example of a definition of a two-dimensional materials. In our literature, we call them quantum well. Okay, so quantum comes because the material behaves, some of the properties can be explained only by the quantum physics, not by the classical physics. Similarly, if you take a chunk of the material along the length in these directions, and both the so-called the thickness and the width is below this de Broglie wavelength or so, below 10 nanometers or so, only the length is large enough. The electron can move freely only in the so-called along the length, and in other directions actually behaves or it follows the quantum mechanics. These are called one-dimensional material, or this is the quantum wire. Similarly, if we just cut a piece from this one and make in all three directions, actually the size of the material is very, very low in the nanometer scale. What you get is a quantum box or quantum dot or a zero-dimensional material. I'm sure that particularly even in the undergraduate course, some quantum mechanics is taught. Particularly, the first problem that we solve in our textbook in the quantum mechanics is a particle in a box. Of course, in that case, we take a one-dimensional box. So, particle in a box is nothing but a kind of a quantum box, and we try to solve the equation of the so-called the Schrodinger equations, and that is normally we see the textbook. But in fact, we will see that it has got a lot of impact on the properties of the material. Not only the size of the material has got some beautiful properties. Even depends upon how the materials, the atoms are arranged in the material. So depending upon that, the property changes. See, the materials can be crystalline, materials can be amorphous. And you know that if the atoms are actually arranged in perfect periodic manner, we call it the crystal or single crystal. If this is completely random, we call them amorphous. If we have something in between, we call some polycrystalline material. And the beauty of this material is that all these three materials behave differently, completely different. So they have taken again a very natural example, again available in the nature. If you take a simple coal made of carbon, actually, of course, there are a lot of impurities in the coal, a lot of other impurities. So forget about that. But the major source of material in this case is carbon. Is basically, that's why if you burn coal, you get a lot of carbon dioxide in the atmosphere. If it's a very, very brittle in nature, you can break it by just some hammer. Same carbon atoms, if it arranged very nicely, actually, this is an example of a graphite. Actually, graphite is nothing but the pencil that you use for writing the notebook is made of the graphite. Actually, you have one of the graphite pieces. In the graphite, you have got a very nice arrangement of the atoms in 2 dimensions, and there is very, very hard along the plane, but can be peeled off easily. You can take one of the graphite, sheet of graphite easily because they are actually van der Waals bonded. But along the length and width, they are actually covalent bonded. So you see, it's a kind of an anisotropic material, same material, carbon and graphite, behave in a different way because of their actually arrangement of atoms. The other example, extreme example is of course the diamond. Of course, diamond we know is a very nice decorative material, but not only that, diamond is a very unique material, exotic material, hardest material available in the so-called Earth's crust, hardest material known so far, and this has got a lot of interesting electronic and optical properties. So it is very costly, of course, because of its very, very low abundance, but it's a very, very hard material. So when the carbon atoms are crystallized in a diamond structure, it is extremely hard. Now these are still, they are actually bulk form. So in this case, not at all actually the lower dimension of carbon. This is still a 3-dimensional carbon, but atoms arranged in a different way. If you take their so-called the scaled carbon atoms or scaled carbon materials, let us see there are a lot of examples. And these are actually some of the examples that actually attracted a lot of attention in the last 30 years or so. and few Nobel Prizes, 2 Nobel Prizes were given in the invention of these materials. And there are a lot of application of these materials currently and even in the future. Okay, so first material is called fluorine. It's basically a carbon atoms, as you see in the right side. The carbon atom is a 60 or 70 carbon atoms actually arranged in a particular, as you see, a soccer ball structure. It's called buckyball structure, and the size of this is in the range of few nanometers. So you see, this is almost like a 0 dimension. In our definition that we have seen that both x, y, z in all 3 directions, the dimension is below. That's so-called the quantum limit. So the fluorine is a minimum material that was prepared in the laboratory by using 60 or 70 carbon atoms with a lot of good properties in structure, conductivity, catalytic property, many exotic properties which does not exist in a normal carbon material. So this is called fluorine, which got Nobel Prize in 1996. The next discovery was on a carbon nanotube. I am sure also you have heard about that. Here you see the carbon atoms are arranged in a particular way, and you have got a very hollow tube whose the diameter of this tube is basically few nanometers in size. So it's a crystalline carbon atoms arranged nicely, and this is you can say nano channel that is created, and that can be used for a lot of actually biological, chemical, gas sensing, and lot of, or even very, very highly conducting channels it can be used. So this was a carbon nanotube, and these are a lot of exotic properties. It can be metallic, it can be semiconducting, and there's a lot of interesting properties. The latest one was about 10, 11 years back. As I said, that you can easily take one of the plane of the so-called the graphite atoms, because they are bonded with a van der Waals bond, very weak bond. So if you take one single layer of actually graphite materials, it is becoming a perfectly 2-dimensional solid. So our definition of 2-dimensional solid was like, in one of the dimensions, the size below the quantum limit. So this is a perfect 2-dimensional solid because thickness of this layer is only about 0.5 nanometer or 0.3 nanometer, etc., like this. So it gives a different kind of material called graphene, and which has again some very, very unique and interesting properties with a very extremely high conductivity, high thermal conductivity. They can be doped, and they can be made a lot of electrical, optical, and mechanical devices. So these are some of the inventions actually made. Just one example that I have taken using carbon, and with the carbon as the element and their nano dimensions. So these are the low dimensional example of carbon. Okay, so just one more example.
Sir, if you interrupt for just a minute.
Yeah, please.
Audience
Please be louder.
Please
be louder. I cannot hear you. Yeah.
অডিয়েন্স আর পার্টিসিপেন্টদের বলছি, যদি কোনো কোশ্চেন থাকে আপনারা প্লিজ চ্যাট বক্সে কোশ্চেন গুলো লিখতে পারেন। চ্যাট বক্স ইজ ওপেন নাও। স্যার উইল বি হ্যাপি টু অ্যান্সার ইউর কোশ্চেন্স আফটার এন্ড অফ দিস টক।
Okay. So, yes, definitely. Please, thank you. All right. So again, one more example. Actually, since I have taken this example, because this example you see in the nature in a daily life, so it's very easy to visualize without going to actually a textbook or even writing a very complicated mathematical equations. This is one more materials made of calcium carbonate. See, again, depends upon the periodic arrangement of calcium carbonate atoms. The one that is brittle is the chalk that you use on a blackboard for teaching. Of course, when the teaching was offline, not now. And if they're arranged very nicely in a crystalline manner, actually you get something called marble. Marble is nothing but a calcium carbonate molecules aligned properly. Of course, there are some impurities there, and they're very hard. They're nicely looking, very costly, used for flooring or in your home. And a natural material, natural calcium carbonate materials like a seashell that we get actually is a very nice color and a very nice, beautiful arrangement made by the nature. And they are not only very hard, they're beautiful. Okay, so this is a really perfectly orderly aligned of calcium carbonate molecule. And if you make them smaller, then definitely you will get some other defined property. Yeah, one more natural example that we take also is which is called actually, this is called, I don't know whether this bar is creating some problem. Yes, the bar should go somewhere because you may not show that be able to see the title of my lecture, slide. This is basically some materials which are, called the lotus leaf. If you lotus leaf, it does not stick water. If you put or it does not stick any kind of dirt also. Lotus leaves are always very, very clean. This is a property of a surface which is called a hydrophobic. The surface of any materials can be, if you put water or if you put any kind of dirt in that, either it can be absorbed or it could be completely repel that. So this is called the super hydrophobic surface of actual lotus leaf. This is a unique property. So the question is that, can we really make any fibers by taking the example of this lotus leaf and make in these things, so that you make something and then if you go to the, rainy season, go outside, it will be never wet. It never needs ironing. Not only that, actually, since it actually does not actually absorb any kind of water molecule. So if you think of the people are thinking that whether we can make a COVID resistance face mask with this kind of textiles, because as you know that COVID, these things, the virus comes from mainly from the droplets, and if the droplets are not absorbed at all on your face mask, everybody is free from this thing. So this kind of textiles can be, lotus leaf kind of textiles can be made. And initially people didn't know that why the lotus leaf behaves like that. But with a modern days microscopy, etc., we can see that lotus leaves are nothing but some kind of a, to see the top, this is a kind of a scanning electron micrograph of a lotus leaf. This is a very, very sharp actually nanofibers. And these nanofibers are very hydrophobic in nature. So this is so people can make in the one who are working on textiles or textile engineers try to make some polymers or synthetic materials which are super hydrophobic like a lotus leaf. The next example probably I can take. Next example I can take is a different colors. Actually, did you ever think that why you can see this color, why the butterfly looks such a beautiful color, and these colors are all different, isn't it? You have got a butterfly with different colors, even different wings have different colors. This comes from a nice phenomenon of the physics. It's nothing but a optical absorption scattering. Now, as I gave you the example, your visible wavelength is about some 400 to 500 nanometer actually. And if you make some material, the surface of the material or the size of the particle is actually much less compared to that, we'll see that the color that you see will be different, because the scattering phenomena actually are determined, actually depending on the size, and the absorption of material will be also different. So basically that what I say, that nanoparticles exhibit different colors because they are small enough to scatter visible light, so they don't absorb. The nicest example that we can take, that if you know the color of the gold is a metallic yellow, is a very nice bright color of the gold. But if you really make the gold, take the gold, so-called the gold, into a very smaller size, these colors are not at all actually that yellow gold color. If the gold particles are of this size, this is of course the size of so-called wavelength of the light, and this is much less than that. Its color looks like a turbid crimson to blue. Then gold nanoparticles with different sizes, actually the color changes. So this is nothing but actually that light is now scattered from these gold nanoparticles in a different way and scattered different kind of light. So we see different colors in our eyes or detector. But please remember, this does not happen only in gold. This happens in all metallic nanoparticles, whether you take silver, aluminum, copper, or even some oxide particles, because they scatter light in a different way. And that is actually a beautiful phenomena. Actually, it's called the resonance of the, because all metallic particles have got metallic particles, or metallic materials have got a lot of free electrons actually, and each of them has got a different kind of density of free electrons, vibrate in a different way. So they have got all different resonance frequency, and they strongly actually interact with the electromagnetic field of the light and give a beautiful color. In fact, if you go to any old churches of, I'm sure that Kolkata church is also there, or any churches in Goa or the Middle East or anywhere, you see different colors of color glasses in old churches or museums. See, at that time, there are no actually nanoparticles are not known, but people used to know how the colors of glasses will be different if you just grind the material to different level and embed in glass. So all the colors originate from actually. So only these theories are known for the last probably 30, 40, 50 years, but the people used to make this kind of color glasses for a long time. Okay, so these are some of the natural examples. So with this natural example, probably I'll go for another 10 minutes or so, and then I will stop probably for more question answers. I'll take the example of your so-called today we are doing. So I've taken a lot of examples in nature. And today what you can do, you can make devices, you can make your communication computations by using this kind of a nanometer size material or objects, which are called low dimensional materials. And semiconductor is the building block of all computer chips, as you know probably. So we have also read, and these are some of the pioneering scientists in the Bell Lab. They got the Nobel Prize for making their first transistor in 1949. So first transistor, NPN transistor, looked like this. I see it's very large in size, in your finger. And then there's about 10 years later, probably integrated circuit or so, some first integrated circuit. And then, of course, we are going on scaling and scaling. So every day you are getting a new computer, new laptop, new mobile phone with a much higher speed, much lower power, and much higher density. So this is the demand of the day. And this is normally I show this to all the students. Of course, that you don't have to understand this, but this is just a this is called a law. Actually, is a law actually first given by the so-called the Moore, Gordon Moore. Gordon Moore was actually the first established the today's Intel Corporation. So you get Intel Insights, Gordon Moore, and two other scientists was actually established Intel. So first CEO of Intel. And what is happening, if you see last 50 years of the so-called the scaling of the materials, particularly for the electronic devices. As you know, in the what we have in a computer chip or in a CPU chip or your memory chip, nothing but a millions to billions of transistors. So of course, if you reduce the size of the transistor, of course, you can integrate pack and pack more transistors on a chip. That's what is happening for the last 50 years or so. In 1970, probably a transistor used to have a gate length. Typically, these are MOSFET or CMOS transistor. The length of the gate between the source and drain was about 5 micron. And today in 2021, commercially, you have availability of about 9 nanometer gate length transistor, which is available in your probably in your to buy a laptop or if you have a nice mobile phone from market. So state of the art commercial today's computer probably have about 5 billion transistors per chip. And okay, that I have taken example of 14 nanometer length transistor probably 5 years back. Today we have got commercially available at a transistor with the size of 9 nanometer. So you see, we are almost going to that quantum limit, because I said if you take a quantum limit is between 5 to 10 nanometer, you are already about a 9 nanometer or so. But of course, that computers are not made of low dimensional material. They are still actually so-called the classical physics. Actually, the rule or the laws holds there. But the problem is that if you take today's transistors, probably will be about today's chip will be about 20 billion transistors, each of them with a size of 9 nanometer, and they work with a speed of about 10 gigahertz, and each of them taking a very, very tiny amount of power. The energy each of them this transistor takes very small, joule. Auto is basically a 10 to the minus 18 joule. But since we have got about 20 billion transistors, if you try to compute the energy is about 260, the power actually, the power that dissipated on the chip is about 260 kilowatt. So why I have taken this problem, please think of that 260 kilowatts of chip is dissipated on your mobile chip or a laptop, so-called the memory chip, or your CPU chip, which is nothing but a area of few centimeters square. So if you try to calculate the power density almost like it will be like a nuclear reactor or a rocket nozzle. So the problem is that question that you may ask, will you be able to reduce the these things any further, or this is the limit? So you have to really think of how to dissipate this heat, huge amount of heat that is dissipated in the actually in your electronic chip. Otherwise, the semiconductor will not work. So that is what can be done in the future. Probably you are already probably learning about or hearing about some kind of a computing in the future. There will be not this classical computer, there will be some kind of a quantum computer, and there are many ways to build the quantum computers or quantum devices. So of course, I have already told you that at the limit of quantum or threshold, we have defined something like this, that when the size of this feature is comparable to de Broglie wavelength or for the Bohr's radius, and in that case, the electrons, so-called, because all electrons are actually responsible for the electronic behavior, they will be no longer a particle. So in your transistor, electrons behave as a particle. Now the electron will behave like a wave. So is this is good or this is a bad? Of course, this could be definitely very good, but you have to change the laws of physics. And this is again a very interesting story. I normally always tell my students, probably you know that electron was discovered by J.J. Thomson and in 1897, and he got the Nobel Prize in 1906. Of course, the first electron, when he discovered, it was all electrons, always a particle. But his son, the G.P. Thomson is his son actually, the Thomson's experiment through the crystal, he proved experimentally that electron can be a wave. Whatever the de Broglie's hypothesis that every things can be either a particle or the wave. So it was proved by the J.P. Thomson in 19, and he got the Nobel Prize in 36. So nice story of father and son about this two nature of the particle. Okay, so I will basically skip some slides in the interest of time, and I will just probably go a little bit faster, because this is towards the research, what the people are trying to do in the lab. This is not my research, but still in some examples I will give. So the basic things that we have learned till now, that we can really reduce the dimension of the material to low dimensions. And if we can reduce the dimension of the materials, now actually you get a new properties. And I will show you one example. And I always tell you that in the quantum mechanics, the first example you take the particle in a box or a particle in a one-dimensional box. So what I have drawn here actually in this case is a energy level diagram. I know in a semiconductor, you know what is conduction band, what is valence band. So schematically, I have drawn a conduction band and a valence band in a semiconductor, and I'm calling them as a potential well, because there is always energy barrier. So if you put electrons in this here actually, and if you put a hole here, you know that conduction band you have got a lot of electrons, and the valence band you have got a lot of holes. Actually, these electrons will now behave as a wave, and hole also will behave as a wave. And from the first principle of quantum mechanics, we know that energy of this electron and hole will not be continuous in nature. This will be actually discrete energy, and this energy is given by this is the n square h square by 8 m star l square. So forget about the mathematics. M star is the mass of the free electron, and L is the width of this well, so-called the quantum well that we can make in the laboratory, and n is the quantum number. Now, what happens? The basic band gap of material is defined as the top of the valence band to the bottom of the conduction band. It was like this, but since the energy has now quantized, the first ground state energy in the quantum, electron in the conduction band quantum will be like this, and whole energy will be like this. So basically now energy will be changed. The band gap of the semiconductor will be changed from bulk band gap plus some of these energies. So band gap will be now tuned or increased. So this is a nice phenomena is called actually quantum size effect. This is exactly what you see the different colors in different size particles. This is also quantum size effect. But what you have done is a marvelous thing. You have made some material which does not exist in nature. Suppose this material you have taken has a band gap of 1 electron volt in bulk. Probably by making them quantum well of thickness of 5 nanometer or 6 nanometer in the laboratory, you can make them 1.2 electron volt or 1.3 electron volt. So basically now you have made a new material which does not exist in the nature. And that is the beauty of these low dimensional materials. And you can go on varying the band gap of this material just by changing the width of the well. So this all can be made in the laboratory. And the nice example that I have shown you here is actually fiber optic. We have this optical fiber, and the light actually you have projected here, and you've got a nice light coming out here. So this optical fiber only actually all these, as you know, all this communication is through the optical fiber communications, and only few wavelengths of the light can actually pass through the optical fibers without attenuations. Suppose, for example, of 1.55 micrometer of light actually is the typically used for optical fiber communications. And now, unfortunately, you have to make a laser source for this 1.5 micron. But that semiconductor material does not exist in nature. So you have to really make a synthetic semiconductor, and you have to make this kind of communications. So that's what is done today. And so similarly, the same thing that you can do from quantum well to quantum dot. And as I showed you the example of the white light that you see in the Kolkata streets, because they're very, very efficient light. Actually, they are made of again, some kind of exotic materials called gallium nitride, and use the quantum wells of gallium nitride to get typically today we got a blue LED and use the phosphor to get a white light, which takes much, much less power compared to incandescent lamp. So I'll end that. Okay, I've taken the example of quantum well, quantum dots, but the same thing you can make you can laboratory, you can make a so-called the quantum wire or nano wires. And not only that, the future is that not only you can make a PN junction only in the bulk material, you can make a PN junction in a nanowire. You can make a nanowire coat with one of them is P type, another is the N type, and you can use the new materials which can be used for making some kind of for sensors, photodetectors, solar cells. Even you can make transistors or like this. So future probably some of the transistors that we get today in our computer, etc. These are actually made of this nanowire kind of transistor. So I will probably stop here because so for the other speakers we're already late. So I had some few more slides, but we'll not go to that. So what I'm trying to say through this lecture, by using that lower dimensional materials, you can make a very unique properties, you can make some novel properties. And if you really, the future that you see, I'm sure the future that we'll see for this next generation of the people, the quantum, even the computer that we'll be using in future will be different. It will be not an electronic computer, it can be a hybrid computer, while it is a mix of the electrons and photons. Because you know the photons have got large bandwidth and a very high speed. So probably in the next 10 years or 20 years, probably we are looking for this kind of computer. So thank you so much for your attention, and I'll stop here and we're very happy to take up some questions from the audience.
Thank you, Professor Roy. Thank you for the wonderful session. Starting from the bulk material, he has shown wonderfully how this size reduction starting from bulk material to the nanoscale, it changes the properties of materials drastically. And he shown very clearly starting from its environment friendly use and obviously it's power friendly use and its picturesque detail about the quantum mechanical explanation of band gap. Everything we have understood very clearly. I think this will be very much useful for our students, because in a 6th semester there is a course of physics of nanomaterials, and sir, your talk will definitely help for better learning of the students. Thank you, sir.
Okay, great to know that now physics of nanomaterials is also in undergraduate courses.
Sir. Yes,
so I hope it will be able to motivate some of the students to come to this research area in future, because it's a really open science. A lot of things are still very open. So encouraging.
Yes, sir.
So,
now I will request our senior teacher, Dr. Narayan Banerjee, to conduct the question answer session. Audience, please write if you have any question in the chat box, and we will try to. And sorry, Professor Roy will definitely try to answer your questions. I would now request Dr. Narayan Banerjee to.
Hello, students are requested to ask questions, and Professor Rai will gladly answer these questions.
ডক্টর ব্যানার্জি,
হ্যাঁ,
স্টুডেন্টরা তো কোনো কোশ্চেন করছে না, আপনি কিছু প্রশ্ন জিজ্ঞেস করুন স্যারকে।
Maybe the students always feel shy, I know that, unless
হ্যাঁ, they are very shy.
if you do one
না
to one
আমি
interactions,
তো
then
আসলে
only-
ন্যানো মেটেরিয়ালের লোক নই, আমার পক্ষে কিছু জিজ্ঞেস করা খুব মুশকিল।
No, what the students can do that, my email address is there, so you can provide them the email address. If they have any questions, then mail, I'll be very happy to answer them individually.
স্যার আমি একটা জিনিস কথা একটু জিজ্ঞেস করবো স্যার।
নিশ্চয়, of course.
বলছি যে যখন আমরা 2 ডাইমেনশন থেকে 1 ডাইমেনশন থেকে আলটিমেটলি 0 ডাইমেনশনের দিকে যাচ্ছি, দ্যাট ইজ কোয়ান্টাম ডট, সেটার পসিবল অ্যাপ্লিকেশনস কি ধরনের হতে পারে সেইটা একটুখানি হাইলাইট করবেন?
হ্যাঁ, তো ডেফিনেটলি মানে আমি যেটা প্রথমে একটা বলছিলাম যে আমাদের যদি ভবিষ্যতে ধরুন কোয়ান্টাম কম্পিউটিং এর দিকে যাওয়া যায়, ধরুন ভবিষ্যতে যে ডিভাইসেস গুলো, যে ট্রানজিস্টর গুলো উইল বি মেড অফ অল কোয়ান্টাম ডট, তাহলে সুবিধা হচ্ছে যেহেতু দ্য ক্যারিয়ার্স ফ্লো অলমোস্ট ডিসিপেশনলেস, অ্যাকচুয়ালি দেয়ার ইজ নো, actually it's all through tunneling, all process takes through tunneling or the ballistic process. So the resistance will be very, very less, and there will be no scattering of the carrier. That is one thing. And not only that, quantum dot lasers এর ক্ষেত্রে আমি যে সেমিকন্ডাক্টর লেজার্স গুলো দেখাচ্ছিলাম, প্রত্যেকটা লেজারের জন্য আমাদের একটা পাওয়ার লাগে, guide the laser with some power. যেমন আমরা এখন যদি অফলাইনে সেমিনার দিতাম, I used to use a laser pointer, isn't it? But I'm sure the previous generation people, if you can say, how can you use a 1.5 volt battery to power a laser? And then that intensity of the laser is also quite good, that laser that you use in the laser pointer. So basically, jeta hoy, when you're reducing the size and when you're making this so-called the quantum dot, and quantum dot is nothing but a mimic, is a mimic of an atom. আমাদের atom যদি ধরি, আমাদের so-called atomic physics or molecular physics atom, almost atom is also like that, only different in size. So যেগুলো হয় that if you see the density of states of these quantum dots is almost very, very sharp and is almost like atomic density of states. যার জন্য যে property আমরা গুলো পাই, whether it is optical emissions by electrical transport, that is of very, very high quality, and that's why actually they are the ultimate solution. So এবং কিছু কিছু device already people have demonstrated that, like infrared photo detectors, night vision camera. We know that we use the night vision camera in the particularly for all our advanced countries to track the criminal and track the terrorists. These are all by using quantum dot photo detectors. মানে খুব low noise, very good quality, and খুব very low power compared to the bulk material.
আর একটা জিনিস স্যার, আপনি একটা এক্সাম্পল দিয়েছিলেন যে 260 কিলোওয়াট পাওয়ার ডিসিপেটেড হচ্ছে পার, তো এটা তো একটা হিউজ পাওয়ার, এই হিটটা কিভাবে ডিসিপেট করে?
Actually, this is the major problem for which we cannot do any more so-called the scaling. The scaling has to stop because of this problem only, unless you have, because এখন যেটা হচ্ছে যে আমাদের দেখেছি, আমাদের যদি ধরুন আমার ল্যাপটপে যদি এখন এই ফ্যানটা যদি কাজ না করে, ইমিডিয়েটলি কম্পিউটারটা স্টপ করে যাবে। And not only that, if you really put your laptop for 10 minutes in your lab, it will be so hot, মানে আপনি নিজেই ফিল করবেন। বা মোবাইল ফোন আমরা অনেকক্ষণ ইউজ করলে আমরা দেখতে পাই যে কতটা হিট হয়ে যাচ্ছে। তো এটার সলিউশন, একটা তো সলিউশন যেটা মেকানিক্যাল ইঞ্জিনিয়াররা বলে হিট সিঙ্ক, they use a heat sink. Of course we use the exhaust fan, but arekta solution people are thinking, there will be some kind of a nano fluids. So we can suppose these fluids, you know that fluids are good, that they can actually conduct a lot of heat and if we make really very, very high thermal conductivity nano fluid, they can take up a lot of heat. So this is the huge problem in scaling of the transistor. In fact, the heat is the main problem, not the other technology. So this is open problem.
Professor Roy, you took me down the memory lane. In fact, my PhD thesis was on thin films.
Oh, I see. Yes.
So I
Yeah,
was
nice to
recalling.
know.
I was recalling those days.
Yes, yes, nice to know that. Right.
I did a lot of work on grain boundary scattering.
Oh, right. So this is what I could not talk in details, but that is what actually the right.
It's
And
one
now
of the
if you go to nanoscale, now to do completely different, of course.
right. There is a question in the chat box for you.
Yeah. Is there any distinct limit
Uh,
up to where we can compress different types of bulk material respectively? মধুপর্ণা দাস জিজ্ঞেস করেছেন।
Yes, yes, that's a in fact very good question. So normally what we do, we don't compress. We use a process called lithography. So lithography is a process where you can basically cut the object to a smaller scale or nanoscale. Just very example হচ্ছে যে আমি যদি একটা কেক কাটা শুরু করি একটা নাইফ দিয়ে, so how nicely I can cut cake into small pieces. That of course will depend upon many things. যে কাটছে তার কত, of course, the skill and obviously the thickness of the knife. So semi three-dimensional materials actually can be cut into very very small size of materials. যেটাকে আমরা বলি basically বলি আমরা top down approach by cutting the material by a process called lithography. And for the nanotechnology, that process is called nanolithography. And this nanolithography is by using electron beam or ion beam, we can really cut the materials to a very very nanoscale. On the other extreme, the chemists build the materials from the nanoscales. Chemistরা যেটা করে, তারা বিভিন্ন colloids থেকে বা বিভিন্ন atom থেকে তারা আস্তে আস্তে material they actually start growing in the laboratory. So there are two approaches. One is the top-down approaches. The first approach I told, using a kind of cutting tool, and the chemists use that approach called the bottom-up approach. So by using a combination of this, and of course there is a limit. Currently, at the current limit technologically, I can say in a top-down approach, people can go up to probably 5 nanometer or so. And for the bottom-up approach, people can easily go to few nanometers. So it is easier.
Another no, there is no other question here.
Okay, thank you, sir, for sharing.
Yeah, there is
There is-
one more question I will answer. The question is that I will read the question: how the quantum wells are connected for a long nanomaterial? Yes, yeah, this is
Yeah.
again a very good question. Actually, all these connections are done by a method called the integration. Actually, you know that the integrated circuits works like that. You grow a lot of quantum wells. So one of the probably proposal was that if you can connect the quantum wells using a nanowire, if you can see, normally if the quantum wells are connected by a thin film connections, and then you start cutting that thin film into very very small object and get some kind of a wire it should be connected like a wire. So these are actually kind of a nano wire connected between different quantum wells. But the beauty of these quantum wells is, as I said, that sometimes, because now when the electron starts behaving as waves, there can be a lot of coupling between different quantum wells. So in many cases you don't need a connection at all. It will be a connection which is a wire free, which will be metal free. This will be, and the transport will be completely ballistic or the tunneling. Yes, I mean, again, a very nice question. As heat dissipation is a problem, can this heat be converted into electrical energy somehow? Yeah, this is again a very emerging branch of science. Is called thermoelectric material. You know, thermoelectric material. You can use the so-called the filter effect, Seebeck effect, to convert heat into electricity. In fact, if you have followed that, this year Nobel Prize in Chemistry has been given to one person from Bangalore, Konishka Bishwas. He's a Bengali. He's from Jadavpur University, did his BSc. He works on this, that we have got a lot of waste heat, of course, everywhere, air conditions, any other machineries, industry. This waste heat can be really converted to electricity by material called thermoelectric material. Now, most of the available thermoelectric material right now is not very, very efficient. Because any technology you develop, it depends upon how much amount of money you are investing in and how much output you are getting. So that is again a breakthrough in material science. Probably it has started coming. So people are making a lot of thermoelectric devices and which can actually convert this waste heat into electricity. That is a huge opportunity.
Thank you, sir. Thank you for your wonderful lecture and wonderful explanation also. And now we want
Thank
to
you so much.
proceed.
Yeah, it was my pleasure. Right.
Thank you, sir. Thank you. Now we wish to proceed for the next session. Our next session is based on the life of an eminent scientist. This year we have chosen the life of, obviously it's a 100-year celebration of Nobel Prize of Professor Albert Einstein. It was on photoelectric effect. All of us know that this is a breakthrough in modern science because photoelectric effect is the starting journey of quantum mechanics. Therefore, the year 1921 is a very much proud and glorious year of science. So it is the century of this Albert Einstein's Nobel Prize. Therefore, we have chosen Albert Einstein's life, and we have with us a very eminent scientist, Professor Chinmoy Kumar Ghosh with us, who will deliver about Professor Albert Einstein. Let us now give a brief description about Professor Chinmoy Kumar Ghosh. Dr. Chinmoy Kumar Ghosh, he is a retired faculty of Indira Gandhi Open University, where he has inter alia held position, held as Director of Student Support Services, National Center of Innovations in Distance Education, and Regional Center of West Bengal and Sikkim. He has taught physics in Scottish Church College and IGNOU. He is an alumni of ISCS Kolkata. He did his PhD from there, and he is a co-author of many books, total 11 books. 4 of them are in the basic physics level, and one is in innovation of distance learning, and 6 in the volume of general knowledge. He has a vast knowledge of physics and in surrounding all directions of science. He has more than 100 publications, primarily in the area of physics and mathematics, education and open distance learning in the form of research papers, articles, and edited literature in the national and international journals of repute. He has been holding membership of statutory bodies of different universities. He is now retired, and after retirement, he has served as a consultant in the National Institute of Open Schooling, TLC, CET of IIT Kharagpur, and he is currently associated with several projects of NCERT. So let us now welcome our multi-talented professor, Professor Chinmoy Kumar Ghosh. Please welcome.
Thank you, Ms. Paul, for the. Am I audible?
Yes, sir.
Thank you for the nice introduction, and I take this opportunity to give my compliments to the organizers for this memorial lecture. My heartfelt gratitude and respect to Dr. Annapurna Sarker for observing and for paying tribute to her parents in such a solemn manner. My heart goes out to the entire team of Bethune College, in particular to Professor Kamalkanti Shom, who had been in touch with me, and the other teachers of this very reputed college. My sincere gratitude to Dr. Mamta Roy, and also to Professor Shomit Kumar Ray. In fact, I got really enlightened by way of his lecture, and also my dear students. Let me share my screen. Are you getting the screen now, or? Are you getting my screen?
Yes, sir. We are getting your screen. Yeah, we can see it clearly.
So, as has been explained by Ms. Paul, that the topic of the second lecture, that's of mine, is about the renowned scientist, Professor Albert Einstein. And there can be several things which can be talked about him. And I have chosen Einstein as the person of the century. In fact, before I go to the lecture, one thing about Bethune College, which I should mention at the beginning of my talk. I had taught, as you heard from Ms. Paul, that I have taught for about 8 years at Scottish Church College, the college which has the closest proximity to Bethune College. But during those 8 years, I have never been to Bethune College. I would have loved to go there, but maybe there was some kind of shyness or some kind of problem of access, and I had never been to Bethune College. But one person I had known and whom I miss too much today, and I remember her with a great sense of reverence, that is our great Nandini. That is the only teacher who I had known of Bethune College, and so I would like to remember her on this occasion. She would be coming to Scottish Church College and mostly would be consulting with my seniors about any new thing added to the physics curriculum, any new experiment, and she would just come with a childlike simplicity to learn about, to question about such things. And at a later stage, of course, she also used to interact with me. And then on one occasion, she was the external examiner and I was the internal examiner for physics honors practical. And I got to learn a lot from her, a teacher to the core. And I remember her with a great sense of reverence on today's occasion. Now, coming to the topic, Einstein, person of the century, where I have written a quote of Einstein: "Subtle is the Lord, malicious he is not." This has been taken from a very authentic biography of Albert Einstein, written by his friend Abraham Pais. And this is about the philosophical thoughts of Einstein, particularly about his thoughts on religion, where he says that the Lord, the God, is subtle, and he is not the one who rewards or punishes. Malicious is not. Of course, I don't want to elaborate on this topic. And as I had been mentioning, that there are several things, several facets of Einstein's personality and his work on which one can deliberate. So when Professor Shom had requested me to talk on Professor Einstein, in fact, I was quite confused and I got intimidated. But following his request, I've tried to prepare a sort of a popular lecture on some aspect of works of Einstein. Because if I recall our famous poet, Rajinikanto Sen, he says that "Tare je Prabhu bolish, dash holi tui kabe." So acquiring that dashatto, the moral right of serving, I have in no case have been able to do that for Albert Einstein, not from the point of view of his philosophy, neither also from the point of view of his work, but still I am venturing to talk about him. And this is the person. In fact, you will be able to see several photographs of Einstein, and this is Einstein in his middle age. In fact, I would not like to depict him from the very beginning with that person with gray hair and sort of disorganized here and a man out of the world, because he had, according to me, a very, very keen observer, not only of the nature, he had been a very, very keen human observer. If you have time or if you have access, you can read about the obituary written by Professor Einstein about one of his colleagues, Paul Ehrenfest, with whom he had worked in Leiden. And you will find that what a keen human watcher was Professor Albert Einstein. Now, when we talk about him as a person of the century, person of the 20th century, what comes to my mind that, like you see in any Hollywood award or any kind of film award, film festival award, or any such kind of award, there are nominations. And here also there were nominations, and there were several nominees, and I'll name the immediate two nominees after Albert Einstein. That is, one you can see on the screen is none other than Franklin Delano Roosevelt, not Theodore Roosevelt, Franklin Delano Roosevelt. And the reason for choosing him, reason for nominating him, was because of his triumph over freedom, over fascism and communism. And according to Bill Clinton, he was the embodiment of freedom. Now, what is so interesting about this gentleman is that, of course, the connection with Professor Albert Einstein. Now, on 2nd August 1939, Albert Einstein had written a letter. In fact, he had endorsed this letter to Franklin Delano Roosevelt. In fact, he was at Princeton at that time, and this is considered to be the most historic letter reaching the White House. And that is about Einstein saying about the preparedness in Germany as regards preparing nuclear weapons. And he wanted USA, particularly he was with the Allied forces during the Second World War, and he wanted them to prepare themselves also for nuclear weapons, but not to apply them, which ultimately happened in Hiroshima and Nagasaki, and you're all aware of the devastation caused by it. It was like that story of Ramakrishna Paramahansadev, where he wanted the snake to sneeze. So he wanted that, and this particular letter, I'm not going to through the text of the letter, but I'll tell the students to definitely, you'll find this letter on the net, which he wrote to Roosevelt on the 2nd August 1939, and which really triggered the Manhattan Project, of whom one of the important players was Richard Feynman, about whom you heard from Professor Ray. So this was a very, very important connection between Albert Einstein and Franklin Delano Roosevelt. And the next person who was nominated, you will be delighted to know, was none other than our own Mahatma Gandhi. And it was mentioned that he was an embodiment of nonviolence, and he was someone who was up for giving power to the powerless. He was a giver of power to the powerless, an embodiment of nonviolence. And this is what Einstein used to say about Mahatma Gandhi, that generations to come, it may well be scarce believe that such a man as this one ever in flesh and blood walked upon this earth. Ever in flesh and blood walked upon this earth. I like this interesting connection between the nominees who just came after Einstein, but then the Time magazine had chosen this Person of the Century award was given by, or the Person of the Century, not really award, because none of them were there at that time to receive such an award, but the conferring upon this particular title was done by Time magazine. And here you can see that particular issue of the Time magazine with the figure of the great old man, the grand old man, Albert Einstein, the Person of the Century. So let me try to talk a little bit about his works in a very popular manner, as was requested to me by Professor Shom. This is the child Einstein at the age of 4 years. He was born at a place called Ulm in Germany. And initially, he was taken to a Catholic school in Ulm. this is Einstein's father, you can see, Hermann Einstein, and on the right of your frame is this is Paulina Koch, the mother of Einstein, and then you can see young Einstein with his sister Maja. That's the whole family of Albert Einstein. They were there at Ulm, and then in 1888, I beg your pardon, he was born in 1879 on 14th of March. 14th of March again is an important date. Important date from the point of view that if you write that in American style, that is a month before the date, then it becomes 3.14, which is the approximate value of pi. And so Einstein was born on the pi day. He was born on the pi day, 14th March, 1879. And by 1888, he had moved into that school which he hated, Luitpold Gymnasium in Munich, because the family had shifted to Munich. Einstein's father, along with his brother, that is Einstein's uncle, had opened a business from electrical appliances. And for that, they had moved to Munich, where Einstein had joined this famous school, Luitpold Gymnasium. More about that later. So this is Einstein's wife, the first wife of Albert Einstein, Mileva Marik, whom she got to know from the early part of 20th century. And she was a brilliant scholar from an Austro-Hungarian family. Of course, she was not a Jew, and the family had problems about accepting their relations. The first beginning was Einstein's sister Maja getting married to that family, and later Einstein got married to Mileva Marik, and it is said that she had helped Einstein a lot. She was a brilliant scholar, brilliant in physics and mathematics, and had done many calculations related to the theory of relativity, which became almost synonymous with the name of Albert Einstein. This is Einstein's son, Hans Albert Einstein, the eldest son, and this is Einstein's grandchild, Albert Einstein, with Hans Albert Einstein and their grandchild. So he became a very eminent and very efficient hydraulic engineer. In fact, he loved to do physics, but then he didn't like the legacy of his father. Every time people asking him that, are you doing physics? What are you doing with physics? And so on and so forth. And so he shifted towards engineering, and he was quite an eminent hydraulic engineer who passed away in the year 1973. And this is the younger son, Edward Einstein, E-D-U-A-R-D, Edward Einstein, but he had a rather miserable life. Up to the age of 20 or so, he was quite brilliant, in fact, more brilliant than his elder brother. But then, you know, that he got schizophrenia, and particularly due to his medication, he had to be taken to an asylum, and he died there in a miserable condition in the year 1965, 10 years after the death of Einstein. And this particular couple, Einstein and Mileva Marik, they also had an illegitimate daughter. In fact, that is not a part of my discussion, but then for the sake of information, I should share this with you. And nothing much is known about that daughter. In fact, way back in 1980s, it came to be known about her. Several people say that she was taken up for adoption, and then there is another thought that she might have died very young of scarlet fever. And this couple got separated. They got separated, and this separation had hit Hans, but it had hit particularly Edward very hard, as I told you, that he died in a very miserable condition way back in 1965. And it is said that after Einstein went to Princeton in 1933, after that he had never come back to meet his younger son, Edward. And this is Einstein's second wife, which you can see in the figure, Elsa Einstein. And in the middle, Elsa Einstein was Einstein's cousin from the maternal side, first cousin from maternal side, interestingly, second cousin from the paternal side. And in the middle, you can see Charles Chaplin. This is a very interesting photograph of Einstein with Elsa Einstein. Now, something about his work. Now, this is Einstein at the age of 14. And this was the age from which he had mastered physics and mathematics to a very good extent. In fact, there are stories, and in fact, there are sort of misgivings that he did not do well in the school. Well, he was not interested in other subjects, and also not that bad in other subjects, because his scale of scoring, if you see his mark sheet, was reasonably good also in other subjects. And as far as physics and mathematics is concerned, he got very high grades, and his favorite subjects were algebra and geometry, so which he mastered from this early age. And at that time, he was attending the school Leopold Gymnasium, which later came to be known as Einstein Gymnasium. Now, his father gave him a gift. Now, there is something which I'd like to say in this connection. The first gift which his father gave him was a compass, a magnetic compass. Now, whenever we as parents give gifts to our child, in fact, we can give him or her anything which he or she likes. And the material aspect of it normally impresses the child. But then we should try to give the child something which arouses thought, which arouses the spirit of inquiry. In fact, in this connection, I'd just like to mention that in Indian Constitution, if you read Article 51A, Item 6, Clause 6, now it is said that we should develop the scientific temper and the spirit of inquiry. And I do not know whether the constitution of any country would be having that. Now, this becomes relevant, particularly in connection with this particular gift, which was given by Einstein's father to Einstein. Einstein would wonder, would look at this compass, and it would find that if you tap it, if you take it here, anywhere, it is always pointing in the same direction. Now, how does it happen? And that used to intrigue him from his very childhood. That used to arouse him within him a kind of spirit of inquiry. So Einstein would always question. Question his teachers. And these were some sparks of genius which we saw in Einstein. That is, one was this always observing the magnetic compass with great inquisitiveness. And then at the tender age, he proved the Pythagoras theorem in his own way. Now, Pythagoras theorem was something which excited him. Now, Pythagoras theorem, we have known the proof of Pythagoras theorem, that square of the two perpendicular sides, sum of the squares on the two perpendicular sides is equal to the square of the hypotenuse. That is fine. But then the brilliance of Pythagoras was that he could relate geometry with numbers. There are a set of triplets like 3, 4, 5. 3 square plus 4 square equal to 5 square. 7, 24, 25. 7 square plus 24 square is equal to 25 square. 5, 12, 13. 5 square plus 12 square equal to 13 square. In fact, on 5th of December 2013, that is, if you read the date, it becomes 5, 12, 13. The entire Manhattan was lighted in the memory of Pythagoras. Now, what Einstein saw in Pythagoras was his relating geometry with numbers. And he always wanted to have the description of nature, like while saying subtle is the Lord, which I had written in my title slide, subtle is the Lord. Now, he always used to appreciate the nature, the way the nature abounds itself with its abundant treasure. And according to him, that nature can manifest itself through physics, nature can manifest itself through chemistry, nature can manifest itself through algebra, nature can manifest itself through geometry. And that was perhaps driving him to think about the structure of the nature, the structure of space-time through geometry. And the first step towards that was perhaps his proof of Pythagoras theorem. And he used to ask all sorts of questions. In fact, the principal of Luitpold Gymnasium had summoned Einstein's father to the school to tell him that your son does not have a future. Now think of the assessment made by the principal of that school, because he would ask all sorts of questions. One of the questions was that if two vehicles are moving side by side parallelly with the same speed, then each one will appear to be stationary from the point of view of other. Now, if I sit on one such vehicle and I look at the other vehicle, and if I am traveling with the same speed as that of the other vehicle will appear to be at rest with respect to me. And then if I go on increasing my speed and if I attain the speed of light, will light become standstill? So this was his question. And you can always relate this question with his concept of special theory of relativity, the way he treated the velocity of light. And once again, I'd invite your attention particularly to the students that always try to be inquisitive, and the particular national education policy 2020 which has come up that talks about this spirit of inquiry. So don't accept anything without totally believing it, and only after getting totally convinced about it you accept something which is taught in that class, because Einstein hated the kind of rote learning which was promoted by that Luitpold Gymnasium. And see, even if he had forsaken the German citizenship, in fact, during the year 1896 to 1901, Einstein was stateless. He didn't have any citizenship during 1896 to 1901. And then, of course, 1901, he got the Swiss citizenship, which he had held till the last day of his life. So despite that, the Munich Luitpold Gymnasium has been named after Einstein. So during all these years, after getting the diploma and after leaving Luitpold Gymnasium, in fact, he was, after getting the diploma at the age of 20 or so, he was trying for some teaching assignment, particularly in physics and mathematics, but that was not easy to come by. And it was also not easy for him to attain the standards at ETH, which has a very big name. It is very difficult to pronounce, but which is the Federal Institute of Technology of Switzerland. And finally, of course, he could get admitted there, but then still he could not manage livelihood. And then he was helped by one of his friends, Marcel Grossman, and his father arranged for a position as a clerk at the Swiss Patent Office. And the picture which you can see, the photograph which you can see, is Einstein at the age of 26 years at the Swiss Patent Office, and perhaps the most famous patent clerk the world has ever seen, because there he worked for a certain phase, and then came the year 1905, which is called Annus Mirabilis. Annus Mirabilis, the year of miracles of Albert Einstein. Albert Einstein, at the age of 26 in 1905, he published 5 phenomenal papers. Actually 4 papers, and I'm making the count as 5, as it is 4 papers plus 1 PhD thesis. So that makes the count as 5, and all that in the year 1905, and that is called the year of miracles. And Einstein says in one of his memoirs that the storm broke loose in my mind during that particular year. Now again, a kind of message to the youngsters that he was in complete isolation. He was in complete isolation at that time. And then he had the treasure of that profound intellect. He had the treasure of that profound intellect, which was by his side and which could not be assessed, or which could not be deciphered at that particular time by his contemporaries. But using the vehicle of that profound intellect, And using that isolation with tremendous concentration, he would be working for 18 to 19 hours per day. And he came out with this 5 papers. And there are other examples. Einstein's most important predecessor, Isaac Newton. In fact, Einstein would keep 3 photographs in his study. Isaac Newton, James Clerk Maxwell, and Michael Faraday. These were the 3 photographs he used to keep in his study. And when you think of Annus Mirabilis of 1905, think of a similar year in the life of Isaac Newton, that is 1665, when there was plague in London, and Newton was forced to go back to his village in Woolthorpe. And again, there also he was in complete isolation, and he came out with remarkable achievements. First, the binomial theorem, calculus, of course, parallelly Leibniz is also credited with the discovery of calculus. Then the famous principle of gravitation. We'll be talking about that when we talk about Einstein's principle of gravitation towards the later stage of my talk. The universality of gravitation, where he could establish that the apple falls towards the earth and the moon also falls towards the earth in the same manner. And then the aspect of composition of light, that white color is a composition of several colors. So all these 4 things in one single year in 1665. And as Indians, we can also take pride, or we can also at least cite the example of Professor Satyendranath Bose, Professor S.N. Bose, who was also in a sort of an isolation in 1924 when he wrote that phenomenal paper, and which came to be known as Bose-Einstein statistics. In fact, a very favorite topic of mine, and when Professor Shom had requested me, I was feeling very tempted to talk about the Bose-Einstein statistics during today's seminar, but then I thought that I'll talk about Einstein as a whole. But then let us remember with great gratitude that person who used to stay so close from Bethune College, Ishwar Millen, and in complete isolation, he had come out with that phenomenal calculation, and which became the backbone of quantum statistics. The quantum statistics, in fact, if we say statistical physics, it might have started with Boltzmann and also Einstein's theory of Brownian motion. But then its journey from classical statistics to quantum statistics took place with Professor S.N. Bose's calculation. And then Professor S.N. Bose was deprived of the Nobel Prize. Nobel Prize remained elusive for him, which I still wonder, whereas several scientists have received Nobel Prize based on Bose-Einstein statistics. And his name is so much linked with Albert Einstein that I couldn't resist my temptation to talk about that. And then I can connect it with the issue of isolation. So in isolation, if you can concentrate and if you can bring together your thoughts, and if you can systematically do some sort of critical thinking, again, this critical thinking is being promoted very meticulously and very prominently through the national education policy. And when I'm saying this, my attention is towards the youngsters. And so Einstein did that in the year 1905. And then let us have a look at these phenomenal papers. This was mentioned by at the very beginning by Professor Bhomik, when I beg your pardon, Ms. Paul, when she talked about the reason for choosing Albert Einstein, that it's the centenary of his Nobel Prize for Photoelectric Effect. In fact, it was a delayed Nobel Prize. It was a delayed Nobel Prize. There are several reasons behind that, and let me not elaborate on that, because that would lead me to talk about politics of Nobel Prize. There is politics in everything we say, and there was politics in Nobel Prize. So this happened in 1921. It should have happened earlier, and it could have happened. It could have happened for any of these 4 papers. It could have happened for any of these 4 papers written by Einstein. On a heuristic point of view concerning the production and transformation of light, the key feature, of course, as you heard also from Ms. Paul, it's the photoelectric effect. It gave an explanation of the photoelectric effect, that light, which was very well explained as an electromagnetic wave so far, was considered to be a stream of particles, and which were called quanta or photon. And this photon, as you know, is a boson. So as long as light will be there, as long as the universe will be there, light will be there, photon will be there, and Professor Bose's name will be there. Time and again, I'm sorry, digressing to Professor Bose's brilliance. So now this light quanta, light emits energy in the form of quanta, it absorbs energy in the form of quanta, and it laid the foundation for wave particle duality, about which Professor Ray had been mentioning time and again, de Broglie's wavelength, and which was established by G.P. Thomson's experiment. And then it also laid the foundation of quantum theory. And of course, very importantly, it provided the explanation of photoelectric effect. The second paper, now the first paper came sometime in May 1905, and then in July 1905, this paper on the movement of small particles suspended in stationary liquids required by the molecular kinetic theory of heat. And the key feature is Brownian motion. Now, I, as a student, when we were taught Brownian motion in the first year, and I was wondering that this is the work of a botanist, and how it figures in a physics text, how it becomes important as a method of study in physics. Now, it became important in the method of study in physics because the atomic theory or the presence of atoms and molecules was taking ground by that time, But there were several skeptics who would not believe in such minute form of matter. And you have seen in Professor Ray's lecture that it's all about the beauty of atom and even the lower dimension of atom. And this Einstein's theory of Brownian motion established that in a big way, that we always say that when we study thermodynamics, we talk about the macroscopic parameters like pressure, volume, temperature, which can be felt by our five senses. You can feel pressure, you can measure blood pressure, you can feel the temperature, you can feel the volume, but this molecular pollution in the atomic dimension, that is microscopic. So that cannot be felt by our senses. But Brownian motion did a bridging between the macroscopic description of the world and the microscopic description of the world. And that was just an observation by Robert Brown. But then when Einstein had worked out the theory, it established the existence of molecular dimension. So that was also a phenomenal paper. The third one, which came up sometime in September 1905, was on the electrodynamics of moving bodies. And this had revolutionized our understanding of physics. In fact, if you read the book by George Gamow, 30 Years That Shook Physics, which contains the history of development of physics and physicists during the year 1900 to 1930, the two iconoclasts of physics, iconoclast is what we call in Bangla Kala Pahar. These two iconoclasts in physics, relativity and quantum mechanics, well, both has the signature of Albert Einstein on it. And it all started with this paper. And the key feature is special theory of relativity. And the idea was that there cannot be two different descriptions of nature, or rather two different approaches towards the description of nature, from the laws of mechanics and from the laws of electrodynamics. And in an attempt to unify them, he came out with his special theory of relativity. I'll try to talk in brief about this special theory of relativity. And then, as an extension of this electrodynamics of moving bodies, the next paper, which came sometime in November, is, does the inertia of a body depend upon its energy content? And that's how inertia, as you know, mass is a measure of inertia. So he would relate mass and energy and would obtain the equivalence between mass and energy and come out with a very famous equation, I think the most famous equation in the history of science, E is equal to mc square. So this was his fourth paper, and which really is the backbone behind the nuclear energy, which is the backbone behind any sort of energy where you have atoms packed together. The binding energy of a nucleus, that proton and neutron, when separated, they have a certain mass, and this total mass is more than when they get combined. Say in the simplest form of the nucleus of the hydrogen atom, proton and neutron combined has a lesser mass, very, very less, of the order of nano, which you heard from Professor Ray. And this difference in mass is called the mass defect. And this difference in mass goes into the binding energy of the nucleus. And this is the backbone of the atomic explosion. But let us not talk about atomic explosion, which caused so much of devastation. Rather, we can think how this energy can be harnessed. In fact, Professor Ray had mentioned about this in his lecture, how this energy can be harnessed for our requirement. So this was his fourth paper. And the special theory of relativity has not only opened the door for getting efficient energy, but also in order to have efficient global positioning system, which we use these days, and several other features in particle accelerators, these find applications. When you saw that famous experiment on 4th of July 2012 of this, what was later called as the God particle, and that also had the name of Professor Bosch attached with it, the Higgs boson, the kind of accelerator that was used in CERN. All those uses the application of special theory of relativity. And along with that, you had his PhD thesis, which was submitted to the University of Zurich on 30th of April 1905 on a new determination of molecular dimensions, and which ultimately gave him the PhD degree. So now, as requested by Professor Shom, in fact, there are multiple areas and multiple dimensions and multiple facets of the works of Albert Einstein on which one can talk. And I thought that I should discuss in whatever little time available. I can discuss about the theory of relativity, which almost becomes synonymous with the name of Albert Einstein. Now, what was bothering Einstein? What was really bothering Einstein? As I told you, that there cannot be two different ways of looking at the thing. The classical way of there cannot be a principle of different principle of relativity for classical mechanics and electrodynamics. And when he was pondering about this thing, and basically, as I told you, that he was working in isolation, and he would put his thoughts together and would discuss with his friends. And the most crucial thing that came to his mind was time. Time is a very, very significant variable. We talk about space and time, like, of course, this program is happening online, but had it happened offline, so in order to describe this event, the notification would have been that the such and such seminar will be held at Bethune College at 5 p.m. of 1st October 2021. So what you are doing, if you say only that the event will be held at Bethune College, then it's an incomplete description. It's an incomplete description of the event. You have to mention the time also. So in order to describe the event, you cannot ignore time. But we have been using to describe event the three space dimension, the three spatial dimensions. So how can we include the other dimension, time? And time has its own strength. It is not like space. In space, you can go forward, come backward, you can go towards right, you can go towards left, you can go to the top, you can go to the bottom. But time draws us forcibly from past to future. Time draws us forcibly from past to future. It is a parameter. It is not like the spatial dimension. And just try to think about the strength of time. What happened when we switched over from the British system to the metric system? What we used to call FPS system to CGS or MPS system. Now in FPS, foot pound second, in CGS, centimeter gram second, MPS, meter kilogram second. So the third one is not changing. So what, when you came from one system to another, you can change, you could change length and mass. We say the three fundamental dimensions are mass, length, and time, but you could not change the unit of time. That is the strength of time. When you have it, in fact, I do not know whether the students who are listening to this lecture have got exposure to the uncertainty principle. In fact, uncertainty principle manifests itself in three forms: momentum, position momentum uncertainty, angular momentum, angular position uncertainty. So far as these are concerned, these are uncertainties. But when you come to energy time, it is the uncertainty in energy, whereas delta T is the lifetime. It has a different connotation. And in fact, it is the homogeneity of time which you read from the famous Noether's theorem. And in fact, this Noether's theorem came in the same year as Einstein's general theory of relativity, that is 1915. She was also a Jew, and that did not get that much of prominence. In fact, sometime on the lighter side, I compare the general theory of relativity and Noether's theorem as two great innings played by VVS Lakshman and Rahul Dravid at Eden Gardens against Australia. And since VVS Lakshman scored 281, well, Rahul Dravid's innings did not get that much of prominence. So Noether's thing came up, and that was in fact recognized by Albert Einstein himself in the same year 1915. And why it is so important, that she could establish that it's the homogeneity of time which leads to the conservation of energy. So this time and the velocity of signal, that was bothering Einstein. That velocity of signal cannot be infinite. There should be a certain limit to the velocity of signal. And so since there is a limit to the velocity of a signal, if you observe a particular event from an inertial frame of reference, and if you observe the same event from another inertial frame of reference, two inertial frames of reference are either at rest with each other or moving with a uniform velocity with respect to one another. And we are talking about the second case, when the second inertial frame is moving with a uniform velocity with respect to the first inertial frame. Then two events which would appear simultaneous at a particular inertial frame of reference will not appear to be so in the second inertial frame of reference. So that is the most crucial thing. Simultaneity is not relative. I beg your pardon, simultaneity is not absolute. Simultaneity is relative. And since simultaneity is relative, time is also not absolute. Time is relative. So Newton had proclaimed time to be absolute, or all the thinkers at that particular time in and around Newton. But Einstein was very much impressed by the critique of pure reason by Immanuel Kant, where he had given the concept of contemporaneousness of time. Well, I'm not going to elaborate on that now, but then this particular thing and the other issues related to the experiments that bothered him, and he came to the conclusion that time is not absolute, and the main reason is simultaneity is not absolute. And when we talk about all these things, again, about the issues of relativity, length is not absolute, mass is not absolute. That is, when you write ddt of momentum, ddt of mv, while doing Newton's second law of motion, very conveniently we took m out of the differentiation and we wrote m into dv dt, that is m into acceleration, but it is not to be in the case of special theory of relativity. And this mass increases with velocity. The mass increases with velocity, and when the velocity assumes the highest limit of the speed of the signal, it becomes infinite. So that particular limit is unattainable. That particular limit is unattainable, and that turns out to be the velocity of light. So velocity of light is absolute and the ultimate limit of speed. So simultaneity is relative, time and time interval is relative, length is relative, mass is relative, but velocity of light is absolute. So these are the most important consequences of the special theory of relativity. But in order to understand these consequences, in order to understand this, to grasp these consequences, you have to have the notion of the observer. So who is an observer? The observer is not like you and me, that someone is moving with uniform velocity and you are looking at rest, and he has a watch and you also have a watch, and that watch starts moving slow mechanically. No, not like that. The observer is a set of synchronized clocks. Observer is a set of synchronized clocks in one particular frame of reference. So in another inertial frame of reference, that has its own set of synchronized clocks. And since simultaneity is relative, the synchronous aspect of these clocks will be variant, and thereby time will be variant. And in order to measure the length of an object, you need to measure the readings of the both ends of the length. Say you are measuring the length of a rod, then you need to measure the length of the both ends at the same point of time. So there should be, the reading should be taken simultaneously. And since simultaneity is relative, I don't know how much I'm able to explain. Since simultaneity is relative, length also becomes relative. In fact, there were very interesting limericks related to these phenomena of special theory of relativity. Limericks are, which we call in Bangla chhora, and those having 5 lines. The first, second, and fifth line will rhyme and will have the same meter. And the again, I'm describing limerick with length, and I'm getting afraid of Einstein, because this is all classical when we talk about the meter here. And the third and fourth line will rhyme and will have the same length. If you talk it rhythmically, it will go like this: the dhara da dhara da dha, the dhara da dhara da dha, dhara da dha, dhara da dha, dhara da dhara da dha. So here it is like this: there was a young man named Mr. Frisk, whose fencing was exceedingly brisk. So fast was his action that the Fitzgerald's contraction reduced his rapier into a disc. Rapier means sword. So the sword was reduced into a disc. So much was the length contraction. This is some fun with the length contraction. And the name of Fitzgerald, in fact, there are so many players in relativity. It's not really the thought of Albert Einstein himself. It is something which the German scholars Weltanschauung, it's a world point of view, which came from the brilliant minds, so many brilliant minds, and Fitzgerald, Lorentz, Minkowski, Michelson, Morley, and several others were players. So this contraction phenomena was also independently arrived at by Fitzgerald, and so it is said Fitzgerald's contraction, and which was established also mathematically by the special theory of relativity. So this is the limerick for length contraction. There are many, and this is the limerick for time dilation. The moving clock runs slow. There was a lady named Miss Bright who could travel much faster than light. She departed one day on the Einsteinian way and came back on the previous night. There was a lady named Miss Bright who could travel much faster than light. She departed one day on the Einsteinian way and came back on the previous night. So this was about time dilation. And then, when I started my discussion, I talked about inclusion of time along with the space dimensions. Now, once this particular stage is complete, once this platform is created, then definitely we can invite time as a fourth dimension. Now, what was holding up? Among other things, what was holding up is the dimensionality. In fact, when you write the distance between 2 points from origin to a point having coordinates x, y, z, then the distance is root over of x square plus y square plus z square. And say if you are working in MK system, then the unit is meter. Now, if you include time, how can you add the dimension of time with that? You cannot add two quantities which have different dimension. In order, you can multiply two quantities having different dimension. You can divide two quantities having different dimensions. Mass can be multiplied with velocity to give you momentum. Mass can be divided by volume to give you density, but you cannot add or subtract two quantities which have different dimensions. So how to bring in that unidimensionality? And this unidimensionality can be brought by a velocity, because just you forget about anything from the point of view of dimension and analysis. If you multiply time with velocity, time with speed, then it takes up the dimension of length. So in order to facilitate getting the dimension of length, you have to multiply with speed. But with what speed shall we multiply? In fact, we are accustomed in converting space into time. How far is Professor S.N. Bose's house from Bethune College? So we say that it's 15 minutes walk, or 5 minutes in a motorcycle, and so on, 10 minutes in a rickshaw. So when you are telling all that, you are telling a distance in terms of time. You are mentioning a distance between Bethune College and Ishaq Million, but you are telling it in terms of time. And while doing so, at the back of the mind, you have a velocity, either the velocity of your walking, or the velocity of the rickshaw puller, or the velocity of the motorcycle. So velocity is the translational factor between space and time. But in order to be but you need one more adjective. It need not only be the translational factor, it has to be the fundamental translational factor between space and time. And in order to be the fundamental translational factor between space and time, it has to be something which is independent of the notion of the source and observer. And such a velocity is the velocity of light. So facilitation of time as the fourth dimension was done by velocity of light, and it is a fundamental translational factor between space and time. And once we are able to do that, time assumes the fourth dimension. Like Professor Ray was time and again mentioning about the problem of one-dimensional box, the quantum mechanical problem of one-dimensional box. And you saw the energy equation which he wrote on his slide. And there was, I like to invite your attention, if you remember that equation, apart from the mass of electron, the length of the box, the Planck's constant, there was that n, which we call the energy quantum number or the principal quantum number. And how many such quantum numbers were there? Only one, because it was a one-dimensional box. For a one-dimensional oscillator, which we call linear harmonic oscillator, there is one quantum number, which denotes its energy. For a two-dimensional harmonic oscillator, there will be two quantum numbers. For a three-dimensional harmonic oscillator, there will be three quantum numbers. For the hydrogen atom, the famous problem which was solved after the Schrödinger's equation came into being. In fact, there are three quantum numbers, n, l, and m. N, the principal quantum number, and every quantum number will point to a conserved quantity. This is important. Every quantum number will relate to a conserved quantity, n to energy, l to angular momentum. In hydrogen orbit is a central orbit, and so angular momentum remains conserved, and L refers to the magnitude of the total angular momentum or the orbital angular momentum, and m is a projection of the angular momentum in the z direction. That's a magnetic quantum number. So only n, l, and m. But then when you rewrote the Schrödinger's equation with time as the fourth dimension, came the quantum number of spin, the fourth quantum number. So you will be able to relate. When you wrote the relativistic equation, you came with the spin angular momentum. Now it was already established in the year 1922. Next year we'll be observing the centenary of Stern-Berlach experiment. In 1922 it was established. It was also seen by Gauss-Schmidt and Uhlenbeck. But that apart, in fact, it got a solid footing in 1922 through Stern-Berlach's experiment, and it's remarkable because next year will be the centenary. But then through the special theory of relativity, you get the theoretical background that how we get four quantum numbers, and that is again because of this enigmatic parameter time becoming the fourth dimension. And then the other consequence, which you can see with Einstein's handwriting, that I told Professor Shom that I'll be using only one equation. I'll not, because he wanted me to make the lecture popular. And so I told him, okay, I'll not use any mathematical equation, but just allow me to use only one equation. I couldn't resist the temptation of showing this equation on the screen, which you all know, of course. But this is in Einstein's handwriting. In fact, when Stephen Hawking had written his famous book, Brief History of Time, he sought the permission from the publisher that he will be using only one equation. He will not make it very mathematical. And he was permitted to use only one equation, and that equation was E is equal to mc square. So this is Einstein's handwriting, and it became so popular that it has been tattooed several times. How much time I have, Professor Shom?
Please carry on, sir. We have not such time restrictions. Please carry on.
So it became so popular that this equation has been tattooed also. Now you see tattoos on every sports person, and those are different kinds of tattoos, but then people have chosen to use E is equal to mc square and the variation of mass with velocities as the subject of the tattoo, which establishes the popularity of this equation. Now, with this particular equation, our thinking about the conservation principle of energy gets changed. Now, as per the classical statement of the conservation of energy, we had energy cannot be created, neither cannot be, energy can neither be created nor can it be destroyed, but it can be transformed from one form to another, the total amount of energy in this universe remaining constant. But with the advent of Einstein's mass energy equivalence, we say that energy can be created when equivalent amount of mass gets annihilated, and it can be destroyed by way of creation of an equivalent quantity of mass. Now, what is that equivalent quantity of mass? Or what is the equivalent quantity of energy that I explained? That proton and neutron, or let us not go to the atomic dimension. Let us, you must have played with two bar magnets, two Alnico magnets. Now, you do this experiment at your home. In fact, you do it from your home if you have two pieces of Alnico magnets, say their weights are about 20 grams or so. And then when they come together, north pole facing south, they attract. Of course, you will not be able to measure this thing in your laboratory. But again, you bring it in your thought process that when they combine and then they get adhered to each other, and you need a strong force to pull them apart. Now, there is a binding energy. And when the magnets come together, the together mass will not be 20 plus 20 equal to 40 gram, but very slightly less than 40 gram. Very slightly less, which I was trying to tell in terms of proton and neutron. Now I'm trying to tell in terms of the masses of the magnets, that it would be slightly less than 40 gram, to the extent of nanogram or even lower order. But then that multiplied by c square is quite a large quantity, 3 into 10 to the power of 8 meter per second. So when you square it, it becomes 9 into 10 to the power of 16 meter square per second square. So then it would be a substantial amount of energy in joule or in electron volt or in mega electron volt. Mega electron volt is a unit which we use for mentioning nuclear energies at the nuclear level. So that is what you are going to get as the energy, as a mass defect, and that mass defect gets converted into energy. And then when you pull them apart, again, you are creating mass. When you pull them apart, you are creating mass because a certain amount of energy gets destroyed. So this is Einstein's mass energy equivalence. Now all this happened in 1905, and then the next decade up to 1915, or effectively up to 1914 or so, this was a period when Einstein had struggled, and in fact he had moved let me skip that part. It's already 8. He had moved from one institution to another, and that was the period of the First World War. He had, just for the sake of your information, let me tell you that this has created a lot of impact. And later, of course, he went to head the Humboldt Institute of Physics and the Prussian Academy of Sciences, and also the director of Kaiser Wilhelm Institute before he shifted to Princeton. Because after the Nazis has taken the reign of Germany, he had shifted from Germany. But then during this period, from 1905 to 1915, he was working on the principle of gravitation. As I told you that the special theory of relativity was relating everything with reference to your inertial frames of reference. But then what about non-inertial frames of reference where there is acceleration? And what would happen in the case of an accelerated frame of reference? And the most vital case of acceleration, the most prolific case of acceleration is acceleration due to gravity, which you get to see from gravitation. So this was something which was bothering Einstein. And then he came up, as I told you, from the very beginning, he was looking for a structure of space and time through geometry. And this particular mathematics of space-time is a very higher-end mathematics using tensor analysis. And from that, he could calculate, he could find out the nature of the geodesic's surface. And what he could make out, let me tell you in very simple terms, that as Newton said, that it is the force between two masses. Now here it is said that if one mass is traveling through space, and if there is no other mass, it will travel along a straight line. If there is no other mass in the vicinity, it will travel along a straight line. But if it encounters another mass, then the space will warp, W-A-R-P. The space will warp. And in fact, if it's a very heavy mass, the space will warp so much so that it would look like a funnel, as it happens in the case of a black hole. The space will warp, the space will bend. And since it is happening with mass, so what is the best way to prove it, how it can be proved? And again, it was the genius of Einstein who felt that, as I told you, that light has mass. Light has mass because it is carrying the quanta in the form of photons, and the rest mass of photon is 0, but in flight it has mass, and when the velocity increases, the mass increases. So in order to make the space work significantly, you need heavy masses. But then the mass carried by light, to be very precise, if it is 1 photon, the energy is h nu. And if you use the equation E is equal to mc square, then if you relate it with mc square, the equivalent mass will be h nu by c square. So h is of the order of 10 to the power of minus 34, and c square is of the order of 10 to the power of 16. So that would make it of the order of 10 to the power of minus 50. So in order to make the space work significantly, it has to be a very, very heavy mass. And a kind of mass that was thought was like that of the sun. But how can we make an observation? How can we make an experiment? Because it was felt and it was proposed by Einstein that light from a distant star will bend around the sun. The space will warp and it would bend around the sun due to sun's attraction. But how to have the star when the sun is there? You can see the star in the night sky, but you can see the star along with the sun when there is a total solar eclipse. The last total solar eclipse over India had happened again on a pi day, in a different kind of pi day, 22nd July 2009. 22nd July, if you write with hashes, it is 22/7, which is again the approximate value of pi. And in the recent past, it has happened quite a number of times over India on 16th February 1980, on 24th October 1995, on 10th of August 1999, and then 22nd of July 2009. But then I don't think it is going to happen in my lifetime over India. So this incident facilitates observing a star in the sky along with the sun, because the sky becomes dark. If you had observed, I had the privilege of observing total solar eclipse, and with very clear weather I had observed total solar eclipse, and the stars which are nearby, I don't remember the names, but they appear near the sun. Now you have to observe that star for nights together, and then you have to observe, thankfully, if the weather is clear. And so this total solar eclipse cannot be seen from so many places. It will be seen on a track where the umbral cone of the sun and the moon meets the earth, and it's a very narrow umbral cone, and in that narrow umbral cone, whichever places will fall, from there you will be able to see the total solar eclipse. And in that particular year, in 1919, this experiment was performed by Arthur Eddington. Arthur Eddington was a great critic of Albert Einstein, along with other observers, other astronomers. It was done in Brazil and some other places on the track of that famous 1919 total solar eclipse. And it was seen that whatever Einstein had predicted, the shift in the direction of the star, the shift in the direction of the star is very much close to that. And with the passage of years, when the observation of this kind became even more sophisticated, every time it corroborated Einstein's prediction and not Newton's prediction. It showed deviation from Newton's prediction, but it obeyed Einstein's prediction. And thus, the principle of relativity, along with the aggregate of the special theory and general theory, it got established. And as I told you, that there were many players. I could not accommodate all of them on the screen. Naturally, Einstein was the central figure. Below Einstein, you can see Minkowski, whose geometry of the fourth-dimensional space had contributed a lot to the understanding of the nature. On the left of the screen is Lorentz, and this particular transformation from one inertial frame to another, initially it was a Galilean transformation, but now it is a Lorentz transformation, because with the special theory of relativity, we have that Newton's laws of motion are not absolutely right. They have to be replaced by a newer laws of motion, and the transformation from one inertial frame of reference to another will not happen through the Galilean transformation equation, but through the Lorentz transformation equation. And on the other corner of the screen, you can see James Clerk Maxwell, who gave those four phenomenal equations that revolutionized our understanding of electrodynamics. And the two other corners, you see Michelson and Morley. In fact, there were several experiments which were called ether drift experiment. In fact, I cannot elaborate on that. And ether drift experiments had several extensions, from Michelson Morley to Fresnel's experiment, Fizeau's experiment, Kennedy Thorndike's experiment, Bradley's aberrations experiment, and all them together had created this Welles-Hahn zoom. And of course, the central figure is Albert Einstein. And then people started pointing, as normally do, that perhaps Newton was wrong. Newton was not really wrong. Science rolls on, and science creates its own understanding with the passage of time. And see the humility of Einstein. See, Newton, Principia came in 1687. Newton was born in the year 1642, the same year Galileo passed away, and Einstein had never met Newton. It was not possible, but he had made this observation, perhaps to the soul of Newton, that people are upholding his idea, and in a way they are rejecting Newton's idea. So you see the humility of Einstein. Enough of this, Newton, forgive me. You found the only way, which in your age was just about possible for a man of highest thought and creative power. The concepts which you created are even today still guiding our thinking in physics. Naturally, when we do calculations in our own real life world, we don't invoke the special theory of relativity mechanics, but we invoke the Newtonian mechanics. And so the concepts which you created are even today, and even the Newton's law of gravitation we invoke. So the concepts which you created are even today still guiding our thinking in physics, although we now know that they will have to be replaced by others, further removed from the, see the spelling of further, F-A-R-T-H-E-R, the superlative form of far, not F-U-R-T-H-E-R, further removed from the sphere of immediate experience if we aim at profounder understanding of relationships, if we aim at profounder understanding of relationships. So this is about critical thinking. So Einstein was a great critical thinker with profound intellect, and that's why he could definitely respect Newton's contribution with a great sense of reference. So such a dichotomy, I just would like to make a passing remark about his family life, that he could have done a little better as regards raising his children. But then this is the particular dichotomy regarding his life, and his works were definitely definitely an outcome of profound intellect. He didn't have any greed for money, and like when the relation between him and his wife, first wife, Meliva Marik, became strained. In fact, he was waiting from 1919 onward, after this famous total solar eclipse experiment. He told that any day I'll receive the Nobel Prize, and as alimony, I'll give the entire Nobel Prize money to you, and which he did. So he didn't have any greed for money. So all those aspects were there. And along with his profound intellect, he attained this particular stature, which has given shape not only to science, not only to physics, but also to civilization. And all his work were really destined to give this particular shape to modern science. I'll just like to conclude with his pathos. As you know, as I told you, that he was without any statehood during 1896 to 1901. In fact, at some stage he was even offered the presidentship of Israel, which he refused, and later he shifted to Princeton, and there he stayed for the last 22 years of his life, from 1933 till his death in 1955. So he says that if my theory of relativity be proven successful, then Germany will call me a German, and France will declare that I am a citizen of the world. And if my theory be proven unsuccessful, then France will call me a German, and Germany will tell that I am a Jew. So that was the pathos of Einstein, which I thought that I'll end my talk. And I thank you so much for giving me a patient hearing. And once again, my heartfelt regards to the parents, to the beloved parents of Professor Sarker, and my humble tribute to Professor Sarker for arranging this memorial lecture and giving me the opportunity to be a part of it. Thank you so much. Okay, I'll stop sharing.
Yes.
Sorry. Is it okay now?
Thank you, sir. Thank you, Professor Ghosh. It was indeed a very wonderful lecture. It's actually really a popular level lecture, and without using just one equation, just in equal to MC square you have told that you have used just one equation, and you wonderfully explained everything using limericks, using stories, and using different diagrams, Einstein's own handwriting. You have explained very much lucidly. Thank you, sir. And in the finishing, you have that controversy of Sir Isaac Newton and Albert Einstein also you mentioned. And very much. So thank you, sir, for your wonderful lecture. It is really understandable for all the undergraduate level students and also our first year students, those who have just completed their class 2 level, class 12 they have just passed, and they have entered in our college just. So thank you, sir. Now it's the time to question answer session. I would now request Dr. Narayan Banerjee, our senior colleague, to take over the session. Audience, please ask your questions in the chat box.
So students are requested to ask questions that Professor Ghosh will be glad to answer your queries.
If anyone doesn't have any question, I have one just interesting question. I have heard about Sir Arthur Eddington. Sir Arthur Eddington, she worked a little about Einstein and Newton's theory. Could you please highlight this topic or say a little bit?
Eddington, a great critic. Eddington and even Paul Ehrenfest at Leiden, when Einstein was there, was a great critic of Einstein. In fact, Eddington had been a critic of our Professor Chandrasekhar. Chandrasekhar got Nobel Prize in 1983 as a US citizen. Perhaps he would have got it as an Indian citizen had not Eddington objected to his theory. So he had always tried to question like Paul Ehrenfest also, and that's how we get the two Ehrenfest theorem, which gives the connection between the classical and quantum physics. So Eddington would definitely not believe, will not accept the principle of general relativity, and so it was planned, and several, in fact, at that particular time, if you see all those experiments taking place with total solar eclipse, it was a sort of expedition, and at that particular time you did not have that many sophisticated telescopes. Radio telescopes were not available, so he planned a series of experiments at different places where you have with different fellow astronomers to be absolutely sure, and then when this was established, then only it was accepted, and overnight Einstein became a celebrity.
Thank you, sir.
When I should have had those tracks of total solar eclipse. Those are there available in the net, and if you see where all those experiments are performed, and most interestingly, to this date, whenever such experiments have been performed with greater accuracy, Einstein's calculation has been proved to be correct.
Sir, one more question from Anuradha Rajesh.
এখানে তো দেখাচ্ছে না।
Chat box এ দেখো।
Yes, can you Anuradha Rajesh asked, can you please throw some light on how the theories given by Einstein was later experimentally verified? Yes, this was by Arthur Eddington, sir, explained. Sir, please. Professor Ghosh, please.
See, experimental verification, phenomena happening at particle accelerators. In particle accelerator, those were experimental verification of time dilation. And once you verify time dilation, now you have to look at it from the philosophical point of view. Once you look at time dilation, and if you can verify time dilation, then time dilation was verified through the particle accelerator, because very high speed can be attained there. In order to make this thing appreciable, there are two terms, applicability and appreciability. So the equation is proper time divided by root over of 1 minus d square by c square. So if c square is a very huge quantity, very large quantity of the order of 10 to the power of 16. So if v is small, so for our day-to-day speed, this thing cannot be verified. This thing is applicable but not appreciable. So in order to make it appreciable, you have to go to speed to about 80% or 90% of the velocity of light, which happens in a particle accelerator, and there it has been verified. And once time dilation gets verified, you have to look at it from the philosophical point of view. Then length contraction also gets verified. Variation of mass gets verified. And then the other applications, nuclear reactors, in the global positioning system, you are using the principle of time dilation. And so far as the general theory is concerned, with the sophistication in radio astronomy and radio telescopy, you can measure very accurately the deviation of the position of the star. In fact, with every total solar eclipse, this has become a routine experiment now. I don't have the data ready with me, but this has been a routine experiment, and without a single exception, this particular law, this particular bending of starlight when it crosses the sun has been verified and has come to be close to the calculation made by Albert Einstein. Does that answer your question?
Yes, sir. Thank you so much.
Yes, sir.
Sir, I have one question. May I ask one question?
Please.
Yeah, Gautam, bolo.
Einstein was awarded Nobel Prize in the year 1921 for the work Photoelectric Effect. But there are many works, I think Einstein could be awarded many Nobel Prizes in his lifetime. But my question is, do you think that Nobel Prize for Photoelectric Effect could be shared with Leonard? Leonard was a discoverer of photoelectric effect. What is your opinion?
Yes, I don't think I'm very much competent to answer this question, but you are right. I also had a similar thought that if it is photoelectric effect, it should have been shared with Leonard when you say photoelectric effect. In fact, they had to give Nobel Prize to Einstein, and they had to, again, that is purely my view, but I'm not quoting any particular reference or anything. And as I told you that in the year Annus Mirabilis, all the works which Einstein had done, all the papers which he had written was worth the Nobel Prize. Even in 1907, when he published that theory of specific heat, the first venture into the quantum theory of specific heat, that was also worth the Nobel Prize. But then they picked up something which had a direct experimental verification. General theory of relativity had an experimental verification. Special theory of relativity has an experimental verification. But then in your laboratory, as you can see photoelectric effect, and even today, as Professor Ray was talking about solar cells and all that, which again is an application of photoelectric effect. So since it has got so much application orientation, it was the safest thing for awarding him the Nobel Prize. That's how I visualize it. I mean, that is purely my thought, because you cannot get all these things documented anywhere so that you can give a reason. But I completely agree with you that if it is on photoelectricity, it should have been shared with Leonard.
Thank you, sir, for your opinion.
Gautam, I think we are a little late. So if anyone has any question, please send to us and we will send it to sir. And send it to your mail, sir. So that
So time dilation has not worked for this seminar.
Sure. So
Okay.
we shall go to the directly to the
Yes, sir.
concluding part.
Yes, sir. Yes, Kamulda. Then we are going to the our final part, that is vote of thanks. I would now request our senior teacher, Dr. Gautam Goswami, to deliver the vote of thanks. Dr. Goswami, please.
Thank you, Rakhi. Just one. We are nearing the end of the program, and I am honored getting the opportunity to convey the vote of thanks. So first of all, I would like to give thanks to Annapurnadi, our beloved Annapurnadi, for initiating this program as a tribute to her parents in the year 2015. And in the last year, 2020, it could not be done due to obvious reasons. So actually, we have spent a very good evening as a result of this enthusiasm. So at the very beginning, I want to thank Annapurnadi. Then I convey my thanks to our respected principal, Professor Krishna Rai. She is a person who is always with us in every activity like this. She gives us the valuable suggestions, inspiration, and always share. Due to pre-schedule, she could not be present to this program. And we thank Dr. Krishna Rai, Professor Krishna Rai. Next, I convey my thanks to the special guest of today's program, Professor Mamata Rai Chundhuri, former principal of Bethune College, and now the Vice Chairman Academics, West Bengal State Council of Higher Education. In spite of her extreme busy schedule, Professor Ray accepted our invitation and stayed with us in the inaugural session. Thank you, Madam. I think it is worth mentioning that we have experienced a wonderful starting session in wonderful world of low-dimensional materials. Thanks, Professor Shomit Kumar Rai, the speaker of the session. We are really enriched to your illuminating lecture. Thank you, Professor Rai, for coming here, though in the virtual platform, obviously, in spite of your extremely busy schedule. Next, I want to thank Professor Chinmoy Kumar Ghosh for giving an excellent talk on the life and work of the person of the century, Albert Einstein. And he very elegantly covered an interesting part of special theory of relativity, and our students and many students who are participating here are benefited through his discussion. And I agree with him. Actually, today we are going on to the session, but we missed something. Professor Ghosh mentioned, we miss Nandini. In every such program, Nandini was always present. And this is the first time in a program we miss her. And okay, in spite of busy schedule, Professor Ghosh is here. We are actually enriched from her talk. Thanks, Professor Ghosh. I also like to thank Dr. Shukla Chakraborty for giving a nice introduction of the life of Ananta Kumar Sarker and Snehalata Sarker. Thank you, Shukladi. It is very important to mention at this point that the Physics Alumni Association of Bethune College, as always, plays a very, very important role in these programs. And this time also, it has been possible to arrange the program, and without that help, it could be, I don't know whether it could be possible before the puja or in the next year, because we are running under crisis, due to the pandemic situation. There are many obstacles we have to overcome. Okay, so thanks to every member of the Physics Alumni Association, Bethune College. Next, I extend my thanks to the Secretary Teachers Council, Bethune College, Dr. Amita Paul. Though we could not listen her due to technical reason, Jantrere Jantrona, due to technical reason, she's a person who is always available with us in every activity like this. And she's full of energy. She gives us valuable suggestions, inspirations. So thank you, Amitaji. Now, special thanks to Dr. Gopal Bhumik and to Dr. Rakhi Pal for anchoring beautifully the program from the very beginning. Thanks to Dr. Narayan Banerjee, Department of Physics, for conducting the interactive session. And I want to mention the name of our HOD, Dr. Kamal Kanti Shom. In spite of extremely busy involvement in various spheres in the college, she gives special monitoring. He gives special monitoring and everything in the process of arranging of this program. So special thanks to Kamalda. I also like to thank Dr. Shanta Bandopadhyay Rajguru and Dr. Saurabh Ganguly, our teachers in the Department of Physics, for their involvement in the program. I am now very glad to mention one thing and to convey my special thanks to our beloved SEM 5 student, Shamoita Dutt, who has prepared beautifully the flyer of the program. So thank you, Shamoita, our beloved student, Shamoita of SEM 5. Last but not the least, I'd like to thank Mr. Akash Mondal of Brain Drops for technical support during the entire session. So again, if I miss somebody, I am begging apology. I have mentioned, and not only that, I have not last but not the least, I want to convey my thanks to every participant from different colleges, the teachers, the students, and also our beloved students of Bethune College for their participation. Thank you all again. Thanks.
Thank you, Dr. Goswami, for this wonderful thanking session. With this vote of thanks, we would now conclude today's seminar. As this is an endowment seminar, this is we don't have any participation certificate. So thank you all for your patience, and we are now concluding the session, and you may leave now. Good night.